Okay, look, welcome everybody. I hope you can hear me. We've got like a minute before the start time, but I'll just say very briefly a couple of words so that we do stay on time. So firstly, it's so nice to see people's faces, even if we can't be together in person, and thank you very much for coming along to the session. The session, among other things, will be looking at how we can learn about the physics of neutron stars and black holes from mergers, but also other kinds of sources. Short housekeeping thing, if I could get everybody to please mute their webcams and their microphones while people are speaking so that the speaker is in lights since it's being recorded. Any questions you have either during or at the end of the presentation, please pop them into the chat box, or please don't hesitate to put up your hand with the little blue hand function. And then the last comment, if I may just say very gently, but also very sternly, we do have to keep really strictly to time because of the online arrangement. The session cancels automatically at the end, so we don't want our last speaker to be cut off halfway through. Okay, with that said, our first talk is from Professor Hendrik van Eerten. Hendrik, are you online?
Yeah, I'm here. Yeah. I go, I guess.
Please go ahead.
Yeah, I was waiting for the starting gun. Yeah, I'm sharing the screen now. We just tested that. Let me now go to the slideshow as well from the beginning. Okay, so I'm going to assume for now that my screen is visible, as is my cursor. Okay, so thanks for the invitation. I'll do my best to give a hopefully informative introduction to how the gravitational waves, which of course is what the majority of this parallel sessions are concerned with, sort of ties in with the multi-messenger aspect of, in particular, long-term observation. So I will be highlighting or confining myself a little bit to the afterglow, and I will get into details about what I mean by that and how that actually can be connected in a constructive way with observations of the gravitational wave signal directly from neutron star mergers. Most of this work wasn't done whenever I refer to my own work as opposed to the work of the community at large. Most of that work is done to a significant extent by a frequent collaborator of mine, Jeffrey Ryan. So I wanted to make sure that his name shows up properly on the slides here as well, because he deserves all the credit for that. When we talk about electromagnetic counterpart observations to neutron star mergers, then we are only, fortunately still only, talking about 1708-17. This image undoubtedly is familiar to everybody involved here. Basically, the point was that we managed, thanks to LIGO, but to no small extent to Virgo, were able to narrow down the error box, aided as well by observations of prompt gamma ray emission from this neutron star merger system, and then subsequently even aided further by the discovery of the kilonova, which of course is in itself an extremely spectacular development of which you can talk for a long, long time, but I will not really delve into the kilonova aspects. It wasn't, of course, a handful of telescopes that did the job here. It was a massive array of observatories. Basically, everybody and their grandmother were pointing whatever instrument they had at hand at this particular source in the sky. So this image from that same paper, which actually includes like half the astrophysical follow-up community in their co-author list, or the plus really does a lot of heavy lifting in the reference there. But that shows in the number of instruments involved. And there were not just the gravitational waves in the beginning, visualized on the top left, and the prompt emission, which popped up briefly 1.7 seconds after the gravitational wave trigger. But that was then followed by the kilonova, which you can see on top right, but ultimately resulted in long-term follow-up campaigns of the afterglow. And the picture that we now have reasonably firmly established is that as part of this process, a relativistic outflow was launched in a directed manner And ultimately that particular relativistic outflow, which may have been responsible completely or in part for this prompt gamma ray burst, is ultimately responsible for some sort of fading afterglow emission that we see across a range of frequencies in the broadband. So just to summarize where we stand, I'll return to some of these slides later on, but I just want to get the complete observational picture out of the way as soon as possible. So we have the overview here. Whereas this previous slide only accounts for the first, well, 10, 15 days or so, and that was, as far as I know, the end of really the informative, at least, clear nova observations. The afterglow observations went on for orders of magnitude more in time, and actually observed a rising and ultimately fading source on the sky, both across the broadband, as I was saying, from radio all the way to X-rays. And this was a remarkable source, not just for being observed for so long, but also for exhibiting a very consistent behavior across the broadband spectrum in terms of its non-thermal emission. So on the left-hand side, you see those rising curves ultimately going down. We have some more data over there, which I'll show in a second. But if you look at the different slots of time, and it's partly obscured by this Zoom IDE I have, or boxes I have over here, but you should be able to see better than I can actually. You can see that there is a non-thermal synchrotron spectrum spanning orders of magnitude frequency that actually has a fairly consistent shape for a very long time, which was also a striking result, not something we're used to when we do gamma ray burst afterglow observations. This actually, this observing of 1717 in the afterglow data, it's still going strong. We have very recent data. We are sort of over here. I forgot the exact number. It should be at, I don't know, 1,300 days or so after the event. We're well over 1,000 days with our data points. So I'm adding this picture just to make sure we are semi up to date in at least now in presenting the different observations. There's two panels here. Again, I will return to these figures briefly somewhat later on. But the difference between the two is that on the right-hand panel, I did not merge the latest two X-ray data points, the black dots, whereas on the left panel I did. And that goes to address the question, is actually something weird happening at late times? Do we actually see a new rising component, yes or no? The blue dots on the same figure are just radio data points that are shifted to demonstrate how well they coincide in their behavior with the X-ray points. And this is, in a way, a manifestation of those synchrotron slopes that are so unchanged over a long period in time. One thing I thought was worthwhile highlighting, because it also plays a role in this expanding this notion of multi-messenger observations to whatever channel, even if they're strictly both electromagnetic messengers, we just want to have them all together and sort of mix their information and extract some sort of joint picture from them. So it should not go unmentioned that there has been a successful campaign at some point. There have been successful campaigns to actually do very large baseline interferometry in the radio. And two publications specifically that I highlight here have managed to do something I think quite impressive, which is to actually find evidence for apparent superluminal motion across the sky of sort of centroid motion at different times. So here you see on the left-hand side, this would be sort of a peak position in 75 days, corresponding to this version on the right, going leftwards in this particular orientation to 200 days. This is a zoom in of this larger image here to ultimately 230 days. So that black cross here represents this red structure over there. And these authors, they both argue that this is another way of establishing that you're looking at some sort of tightly collimated jet that is not really seen directly on axis, but actually at somewhat of an angle, and allowing for this apparent superluminal motion effect. There are some caveats there, so I'll keep putting little extra references here on the bottom of the screen if there are caveats or interesting points to be made. The statement that you see a tightly collimated jet is a little bit sensitive to how you perform your computer simulations, what you put in your computer simulations, what you assume for the dynamics by computer simulations. I now mean MHD or RHD simulations of emerging jets or expanding jets. So a ton of things, obviously I'm not going to do now, but a ton of things can be done with multi-messenger observations of an event like 170817. And there are all sorts of questions one can ask, and sometimes, of course, answer very straightforwardly, if not directly. The question, what merged? Yeah, that we know because we fit the templates for neutron stars merging, so we know that. Some questions are deceptively simple, but may, through loopholes, end up allowing for alternatives. One of these would be, what is the fate of the remnant? I'm not an expert here, but the debate whether or not a black hole was formed has not been completely closed. I think most people would sort of say, well, it's probably a black hole, but there are some interesting footnotes to that statement. And other questions which I think even will be addressed in some depth later in this parallel session, like what is the neutron star equation of state, are of course also of great interest to try and resolve using multi-messenger observations. One thing which I will sort of use as a narrative thread through the presentation now is mostly what is the orientation of the outflow, because that sort of connects to the question, what is the distance to the source, on account of this degeneracy between distance and orientation that one gets purely from the gravitational wave observations, and what this potentially implies for cosmology. I'm not going to go into the cosmology itself, but the point I think is useful to make that of those 3 bullet points, you can move in one direction or other depending on your preference. You can assume cosmology and doing so nail down the orientation of your system, or you can just try and go the other direction. And for just 170817 alone, this is not really a high precision constraining cosmology yet, but it, my understanding is that suppose in the future we have a reasonable set of EM counterpart observations or neutron star merger observations that allow for this kind of analysis, that gets a lot better. Other questions, of course, relate to the kilonova. Again, I'm not going to go into these in depth, but one question that sort of relates to this orientation question is the question, do we actually generate a jet? And this may be a question that is mostly originally of interest to the gamma ray burst crowd, because gamma ray bursts, those prompt gamma ray emissions from these neutron star mergers, were actually only theorized to be from neutron star mergers and had never been observed directly as coming from neutron star mergers. The evidence had always been indirect, and this is by contrast to a different class of gamma ray bursts where the prompt emission would last for longer and for which corresponding supernovae had been found, which sort of clinched the connection to collapse of massive stars. But the merging of neutron stars, we only had that smoking bullet thanks to 170817. As I was saying, I plan to use this as angle thing as a bit of a narrative thread through the story. So here I highlight from this earlier massive paper, or one of the series of papers, the actual constraints one gets on observer angle from the gravitational wave observations directly. And it is telling, of course, that if you use extra information, you can quickly improve the constraints one gets. So if you know where in the sky the source is, and here in this case you can just use the location of NGC 4993, you can constrain the orientation of the system to a more tight constraint, which is roughly less than 28 degrees. And by orientation of the system, I now mean the orientation between the actual jet or the normal on the plane of merging and us as observers. So this would be 0 degrees if the jet were launched straight at us. One thing one hopes to do, of course, if it comes to multi-messenger observation, is to then take that information and merge it with the other channels of information we have. And I think I ought to highlight at least this recent paper. It's sort of a stand-in for other works, and it's a very good showcase for where we are heading now as a community when it comes to electromagnetic follow-up and modeling of electromagnetic follow-up, which is that you can take constraints you get from, say, the gravitational wave observations, like the chirp mass and the mass ratio, and see how these connect to features of this complete system. And here, this diagram also illustrates all the stuff that's going on, right? We have a merger plane. You would have various types of debris ejection and wind and dynamical ejecta and all this kind of non-relativistic or at most trans-relativistic outflow related to the kilonova itself, together with jets being formed. In this case, is bipolar jet flow, which may or may not come with extra features on the edges. And all this rich phenomenology of features is ultimately model dependent on what effectively sets the initial conditions for this launch, which is the gravitational wave system that is merging. So this particular group has made an effort to start to combine the signals from the different channels. And they end up concluding, for example, about the angle of the system, that you're about 27 degrees or somewhat lower, depending on what exact model you put in. But the key thing to highlight here as well is that this is, this is a very good recent result, but it does depend on the prior one puts in the beginning. One of these aspects of this priors is that you want to also put in not just kilonova stuff, but also the actual jet stuff that people have modeled. So I will be spending some time on discussing that in some depth. And there are various lessons to be drawn from this afterglow picture that emerged over the decades in time. Well, that sounds like we've been doing for 10 and 10 years, but I meant, of course, orders of magnitude starting at this seconds. And the first lesson is there actually was an afterglow. Not only was there a prompt emission, but there was an afterglow. And this sounds like an obvious statement now, but in the beginning, it wasn't obvious whether or not there was an afterglow. We are used to a situation observing gamma ray bursts that we're looking straight into a jet, and we sort of see a jet fade out immediately as it sort of dissolves into the environment. And that would be this gray curve going down gradually. Instead, we didn't have that. We had upper limits, like here shown, swift upper limits. And only later on, thanks to Chandra, we would find a few actual detections in the X-rays and some detections in the radio at similar times. So that immediately tells us something that, oh, we may need to wait a while to get this kind of afterglow signal. And the reason this changed our picture for, it was a bit of is a bit of a change of gears for gamma ray burst modelers, is that we are used to take this picture of looking straight into a gamma ray burst afterglow jet. For example, oh, maybe I should stop that because I haven't even told you what's going on here. The yellow dot or blob is the emission shown by a jet. We're looking straight into that jet now. It's actually the this measure of the inverse opening angle here. Whereas the gray circle describes, due to relativistic beaming, what of that blob we can actually see. So we can't see the full blob in the beginning. We have no idea we're looking at a jet. But if we wait a while, then, oh, the movie stopped. How do we do that? There we go. If we wait a while and this gray circle grows to encompass ultimately the entire jet, we realize there's nothing outside of the jet and the signal changes as a result. So you would get a slightly different slope. That's the usual picture fading down from the beginning. But if instead we move our observer off axis, what one would get is a different picture where at first you're not seeing anything because you're not seeing this jet from the get-go, but ultimately the jet comes into view and then fades out of view. And it's only this setup that allows you to generate an off-axis afterglow that in terms of its initial behavior is reminiscent of what we then saw after 2 weeks. And then again, you can have analytical approximations for what these slopes are like, as well, including a measure of how tightly collimated the afterglow would be. Now, the second lesson is that's nice and well, but that is a story that is about these first few data points. In practice, we actually had data points that kept on rising for a longer time, like so in the X-rays and like so in the radio. So that meant that we had to modify our models. And one thing one could do would be to say, well, we just discard this jet notion. Let's say we don't actually have a jet. We have something that actually dissipated within the kilonova debris, within the ejecta, and ultimately came out gradually in terms of a quasi-spherical outflow. That would be one option to account for a gradual rise. Another option would be to say, well, we can actually stay with the jet picture, move ourselves off axis. And that was one of the options that was already there in the first few papers, as you can see by these different curves on the right. So it wasn't a novel idea, but it was something that became inescapable. Oops, as are these movies at the moment. Okay, that became inescapable if you have multiple points of observations here. So I'm actually looking at my clock. I'm seeing I'm going a little slow. I may speed up or skip a few slides later on. Anyway, the notion of having therefore some extra structure in the jet is something we may want to include. And that works out quite nicely because you can get a more gradual rise according to the same kind of analysis. If you have a tapering off energy as shown on the top right over here with angle, and then get to this more gentle rise. So that works out fine. Not only does it work out fine, it is actually something that is not retrospectively destroying our afterglow models that we used to deploy, because when you look on axis, this structure is not really visible. It's an afterthought. It's just some fluff at the edges. But if you move off axis, the story changes, and only then does the structure become very important for the afterglow picture. It is also something that we can reasonably expect to happen anyway. If you run a computer simulation of a system that is in the process of merging for the purpose of generating these kind of jetted outflows, you always get some jet structure. You never get jets that are purely confined in their energy within a certain opening angle and then drop to zero immediately. That's nonsense. That is a toy model. So here on the left, you see all sorts of different computer simulations with and without kilonova debris to scope the structure. Sometimes you just can get there purely from the torus interaction. And they all have, according to these gray lines, profiles that match reasonably straightforward parametrizations. And it's those parametrizations that many groups use to pinpoint the nature of the jet. And if you do so, you can basically build up the signal over time from these top hat or simplified models that you then combine into multiple analyses and end up with a gradual rise. And that is something that one can actually link to some statement about the rising slope. It's not that hard to actually derive immediately from the observed rising slope some measure of the orientation of the system, which again, ultimately one hopes to tie in with, say, cosmology or any distance measurement. It also works for the prompt emission, which is very interesting, but which I'm going to skip on account of time. But I guess I can make the main point, which is that this structured jet model would sort of help you in getting the exact prompt emission energy scale right. It turns out to be fairly faint, even if you, it turns out to be quite hard to really get there with just beaming arguments. You have to sort of split the difference, but again, I'm going to skip that slide on account of time. Another lesson that this afterglow picture tells us is that we may at some point see a downturn. Of course, we now know that we've seen that. And that downturn will be quite telling, because that will be far steeper for a directed flow, a collimated flow, than it would be for this kind of dissipated choke jet model. So that was a thing that we proposed quickly, early before that actually became apparent. And it has very strongly vindicated. That is, if you wait long enough, you don't, if you get like one extra X-ray point and you find a strain in the middle, then you're not there yet, but you have to wait a little bit longer. And ultimately you find that you get the right slopes, because those data points now are at a slope, a downturn slope that is too steep to be reconciled easily with this kind of choked, dissipated flow. And at that point, we sort of know that we're dealing with a collimated outflow. And this comes on top and independently from those centroid motion arguments. Now, if we go to where we are now, this is actually an interesting time, because it may be that there is a novel component emerging. This may be an echo or an afterglow-like feature of this kilonova debris, which at first showed this almost thermal-like emission during the actual kilonova stage, which all these fantastic lines and so forth, but later on would show non-thermal synchrotron-like afterglow emission as well. this is the kind of stuff we then model in some depth. You take a model and you just run through model parameter space until you have a good handle of the probability distribution function and the posteriors of the parameters that you put in your model. And if we sort of interpret these in degrees, going back to what we had initially in terms of the opening angle of the system, or sorry, as the orientation of the system as we got it from the gravitational waves, we end up with numbers that sometimes are a little bit high, if this is not really equal to or lower than 28 degrees, as we at first argued, and sometimes just hits the mark completely, in particular when you, for example, include an extra component emerging at late times. You can get to sufficiently narrow opening angles too if you just take a jet that doesn't spread, but that is sort of cheating because jets will spread eventually, and that's a bit of a word of caution. If you sometimes see people in literature take a fantastically sophisticated, impressive model of the early stages and then extrapolate this to many orders of magnitude further in distance without accounting for spreading. You can put an extra component in there.
We're into the question time.
Okay, let me then wrap up in a few seconds. That is okay?
Absolutely.
Okay, so I'm getting to my punchline. I won't dwell on this one, but this sort of goes to this question: is there something extra happening? Or depends on whether or not you re-bin and what the tension actually is if you do the modeling in a sufficiently thorough manner. But let me, like I said, get to sort of my punchline slides. I have here a bit of a duct-taped animation because I just go between slides, where I show what happens to the posterior, only of a subset of parameters, if you look over time. So at first, at 180 days, we are beyond this turnover now, but not that far beyond the turnover, which happened at 160 days. We still have a broad posterior, in particular on the orientation of the system, purely from the afterglow observations. And that one kept on creeping upwards as the system was observed at later and later times. And this becomes problematic when it comes to reconciling it or post hoc reconciling it with gravitational waves. If we instead do this exercise, including the multi-messenger story, including what we knew from the gravitational waves, we have a far more well-behaved posterior. We have this 19 degrees, which is well in line with what one would have in a way you sort of put that in there by as a prior. Well, that's literally what you do. And you then go on over time and you see that you now end up with a model which again pushes towards a very awkward orientation, but we can still improve on that by either fitting for this extra luminosity component that gets us in the right direction, or by including in our fit the actual motion of the centroid. This is, like I said, this punchline I was getting to, where you want to include as many channels as possible. And I think that is where I should stop. So I'll leave you with the conclusions, and I apologize for going over time slightly here, but I'm happy to take questions at this point.
Thank you very much, Hendrik. Very interesting talk. We do have 2 minutes for questions for Hendrik, and I see a hand from Asaf.
Yeah, hi. Thank you very much for an excellent talk. I have one question about this jet structure that you were showing. As we know, there is this very nice simulations by McFadden that show that even if you start with some structured jet, then after a while the jet starts spread sideways, which pretty much wipes off the initial differences in velocities at different angles. Of course, that depends on the energy that you have and on the density. So can you put some constraints on the density based on this measurement of the structure of the jet after quite some long time that you have there?
Are you talking about the density of the system within which the jet emerges?
Yes. The
yes.
ambient, of course, yeah.
Yeah, of course we do. Yeah, that's part. I mean, I should probably have a slide here that has. There's tons of parameters here, and I don't know if it's visible, but this one is the density included as well. So you do the full fit, and you have, in this case, density of 10 to the minus 3-ish, 10 to the minus 2.7. So yeah, all those different simulations get to include statements about the density. The differences between the simulations ultimately, as you were saying, sort of become less extreme once you pass the turnover point, you are no longer really worried about the structure of the jet. The structure of the jet is what sets this rising slope. Post turnover, you're just looking at a fully visible jet, and in gamma ray burst parlance, post jet break.
That's at 10 to the minus 3 particles per centimeter cube. That's very low.
Yes, but this is of course a short GOB.
Still, okay. All right, thank you.
Okay, thank you very much for the question. We are out of time, but can I please urge people to put their questions into the chat box, and I'm sure that Dr. Van Eerten will be happy to answer them. Thank you very much, Hendrik, for a great talk. The next speaker on the program is Dr. Lazaro, and she will be talking about signals from the post-merger period from black hole binary mergers.
Can you hear me? Can I share the screen?
I can hear you clearly.
Okay. So now the screen should be shared and
Yes.
in full screen mode.
Yes, perfect.
Okay, so the talk is about a methodology to look and search in the post-merger and post-ring down phase of after the binary black hole coalitions to look for possible signature of signal outside the general relativity prediction. This work is part of the PhD thesis of a student in Trento, and is done by the PhD student, me, and people from Trento Group, Rome, and the University of Zurich. So why search for the post-merging search in the post-merger phase of binary black hole coalitions? But we know that in the last year we had many compact binary coalition detection, and most of them, more than 30, sorry, are in the for sure BBH range. So with a mass that that can led us to declare that are binary black hole. Then there are different astrophysics, theorized astrophysics process that can foresee or predict a signature in the phase, in the post-merger ring down phase, post-merger and post-ring down phase. Probably the most known, the most famous is the echoes, and there are many papers in literature that report on this kind of theory and the typical feature of possible echoes. But there are also other astrophysics process that can bring to a signal in the post-ring down phase. One is for example, there is a really interesting paper that discuss about the possibility to have a small chirp after the merger, depending on the mass ratio of the asymmetric compact binary of on the post-merger phase of in case of asymmetric binary system, and in case of spatial orientation of the binary system with respect to the observer. So there are in both these science case there are the possibility to observe in the post-merger in the post-ring down phase a small signature with the chirp feature or something like more ring down or Singh-Gaussian morphology. So probably the most interesting case is clearly the case of the echoes. So there are a lot of alternative model for black hole that describe the black hole as possible exotic compact object as gravastar, spiral, stuff like that. And in all these cases, the signal due to the coalitions of binary system form of this kind of exotic object is the same as the signal predicted by the general relativity in the merger phase, in the spiral and merger phase, so till the coalitions. But after the coalitions, there is the possibility, and then after the ring down also, there is the possibility to have some small echoes that should have a morphology that is similar to the chirp, but with a smaller amplitude. So in the paper reported, and the credits is clearly due to the paper, there are a template that includes some predicted echoes. We can see that a parameter that characterizes this part of the signal is the distance between the echoes, is the distance between the first echo and the time of coalitions, and the amplitude reduction factor. So these are the most important parameter to characterize this kind of signal. What we have done is use the coherent wave burst, that is a pipeline that search for unmodeled gravitational wave signal used by LIGO and Virgo collaboration, and we have tried to set a search based on this pipeline specifically for the echo signal. I don't want here to spend time to describe the pipeline. This is just a standard slide to report the main idea. So I want just underline two couple of important points. One is the fact that coherent wave bursts search for excess power in the time frequency map of the signal. This means that there are no template, and not signal used to search for, but is unmodeled, and we are looking just for excess power. The second point is that the second important point is that the selection of the pixel with an excess power can be done with a slightly modelization. So we can search for pixel that follow a kind of path, but for our search we are performing a totally unmodeled search. So we are looking for the event that CWB is able to reconstruct in the coalitions phase using the ramp up or the chirp up shape, but we are looking in a totally unmodeled feature. So we have set this pipeline for this specific search, and the idea is clearly try to search for a signal that has at least a part of it that strongly deviate for general relativity. So this part cannot be catch up by the template model, and this is the reason why we start with the CWB. And in this example, I report a simulation, a signal simulated and reconstructed with CWB, and it is a typical BBH signal with mass and parameters similar to the detection GB150914. I have reported the reconstruction, and just to understand how the tools works. So the main plot is the reconstruction of the light load, so the selection of the pixel. When the pipeline detect and reconstruct an event, obtain the plot that is on the top of this slide. So this time frequency map with just the pixel selected. And then starting from this map that is built coherent across all the detector, it can reconstruct the waveform, the signal waveform in each, separately in each detector. With respect to the standards use of CWB, we try to optimize the pipeline for this search, and for this reason, we use the fully unmodeled search. We use a set of time frequency map resolution specific for this search, and we decrease at the minimum level possible the coherent energy threshold to clusterize the pixel. Because the idea is that we are looking for just the post-merger phase, and we are sure that the detection of the event at the coalitions phase is a significant detection, because it is guaranteed by CWB, by another search of CWB, or by the template search. So we can decrease a lot the level of the minimal energy to try to collect every pixel with an excess power. Using this configuration, we define a statistical estimator to identify the post-merger signal. And so we define the signal-to-noise ratio, that is the standard statistical estimator in the gravitational wave search, but measured just in the post-ring down windows. So to define the post-ring down windows, we have two main parameters. One is the distance with respect to the time of coalitions. One is the amplitude of the windows. Both the parameters are clearly it is possible to configure it by the user, and we perform many tests. At the end, we decide to work with a 0 to second distance from the T coalitions as the beginning point of the post-ring down windows, and we decide to start from one with the length of the windows of 1 second. This because the most part of the theory that foreseen BBH echoes predicted at least the first echo before with less than 1 second distance with respect to the T coalitions. Then, due to the fact that we decrease a lot the level threshold energy to try to collect a lot of pixel, we decide to add a network coherence threshold just measured in the post-ring down windows. So we use a standard methodology that we use in the CWB to evaluate the expectation of this kind of statistical estimator. We perform a lot of injection using the Lal inference posterior sample. So the template expected from the GR, we injected in the data that's surrounding the BBH detection, and we build the null distribution of this statistical estimator, or better, the null distribution foreseen if the signal perfectly follow the general relativity, and then we calculate the p-value of the on-source estimation. So we perform a lot of simulation, then to search for estimate the sensitivity to the echoes using Lal inference template plus a couple of signal, as it is visible here, adding a couple of signal, chirp signal, BBH signal, or Singh-Gaussian, to look for the capability to detect this. In this case, the signal is extremely high, with high energy, but the HRSS amplitude of the signal in the post-ring down windows range from the same HRSS of the main signal to 1/20, less than 1/20 of the primary detection. So this is the
2 minutes, please, Claudia.
Yes, I have 3 slides, so should be on time. And this is the first result for detection performance. This preliminary result using LAL inference template for the GW1500914. In red, there is the signal amplitude in the post-merger ring down post-merger windows if we include the signal. In blue, there is if for the template that followed the general relativity, and we see that the measured SNR in these windows for the GW1500914 is 0.74. So it's definitely as it is expected by general relativity. Then if we have a look at the reconstruction capability, so which is the efficiency of this method, we plot the detection efficiency as function of false alarm probability, and we can see in this plot that we can reach a false alarm probability of about 5%, with a threshold in SNR of about between 3 and 4, and in this case we will have a detection efficiency of about 50%. And last point is the fact that we have also implemented a method to characterize the signal in the post-merger window. So there is a filter that search for the peak of the signal and found the peak, the SNR in this peak, and the time with the respect time of coalescence. In this simulation, we injected 2 signals, 0.3 and 0.6 seconds with respect to the time of coalescence. And in this plot, it is reported the time at which the filter found the peak, and we can see that the time is perfectly reconstructed. Conclusion, we had a new methodology to look for energy and signal in post-merger phase. We estimate false alarm efficiency for this methodology. We are now working to repeat the same analysis overall, the GW detection. The plot, if you are interested, report about 4 different events. As we can see, the method is slightly dependent on the primaries, on the detection that you are considering, but is not dependent on the signal morphology injected in the post-merger. And that's all.
Fantastic. Thank you very much. And thank you for keeping to time. So we have 3 minutes for questions. Please raise your hands or type into the chat box. While we're waiting, Claudia, I had a quick one on your second last slide. You said that you measured the signal coherence. Could you define that, please? What exactly?
It was here. The coherence the coherence of an event is by definition when there is when CWB select the pixel, there is the energy, the excess power of the pixel, and then there is what we call a null component. Okay, so it's the noise. And so the coherence of an event is defined as the energy coherent across the interferometer divided by the coherent energy plus the noise. So if there are, with respect the total energy in a time frequency region, if the total energy is dominated by coherent energy between across the detector, it is a good signal. If there are a lot of noise, is most probably noise or background event, something that is not related to the signal. And
great.
the coherent across detector is given by the antenna pattern of the detector, clearly.
Yep. Okay, thank you. Yeah, no, that's very clear. All right, I don't see any hands or entries in the chat box. So again, if something comes to the audience afterwards, please don't hesitate to put it in. I'm sure the speaker will answer. Thank you again very much, Claudia, for an excellent talk.
Thanks.
The next speaker is Andres Roshmai, and he will be speaking about stable mass transfer and stellar winds in the formation of gravitational wave sources. And you're muted at the moment, Andres.
Yes, hi.
Now you're clear.
Yeah. I'm trying to share my screen, but it doesn't allow me.
We can hear you clearly.
Yeah, can you hear me? Because I'm trying to share my screen.
Yes,
for some reason it doesn't allow me. Just give me a second. Okay. Okay, can you see my screen?
Yes.
Okay, sorry for the delay, there was a problem. Thank you very much for the opportunity to give this talk. I'm Andres Roshmai. I'm a PhD student at the University of Birmingham. And with Silvia Tonan, I worked on this project titled Importance of Stable Mass Transfer and Stellar Winds for gravitational wave source formation. Unfortunately, I won't have time to talk about stellar winds. So if you have any questions, please just ask later. So just to give you a few words about the line of research we are in, we are actually interested about the massive stars. So that's why we want to use gravitational waves to learn about massive stars. It might seem a bit indirect way to learn about these objects, but please keep in mind that massive stars are very rare, as indicated by the initial mass function, and they also are very short-lived. On the other hand, they are extremely important for a bunch of interesting astrophysical processes. So if you want to understand their lives, you have to keep in mind that 70% are probably interacting as inferred from observations. So you also need to understand their binary interactions. We know that at least some of them will form merging binary black holes. So we can actually use the population of the observed merging binary black holes from LIGO and Virgo to try to say something about the uncertain processes that these stars go through. So there are many proposed channels for this formation of such objects. At the end of the day, you need two black holes that are close enough so that they can merge within Hubble time due to gravitational waves. So they can form separately, can be brought together by dynamical processes, such as it can happen in dense environments, global clusters, but they can also form from isolated massive binaries. In that case, a key point is to keep in mind that such systems typically need no more than a few 10 solar radii of separation to merge within Hubble time. So if you just naively put two massive stars together at such a separation, you would probably, these systems would probably merge just even before they would form black hole binaries. So they need to start out from a larger separation. So there needs to be some process that eventually shrinks this object to a few tens of solar radii. And there are two processes typically mentioned in the literature. One is a common envelope, which happens after unstable mass transfer. So in this case, you have the envelope of the donor, the core of the donor, and probably a black hole. They're rotating in the envelope, and that envelope exerts friction, which can shrink the orbit. It's very uncertain, but even by a few thousand solar radii, and if the envelope ejection is possible, which again is very uncertain, they can end up with a very tight black hole binary. Another process would be through stable mass transfer. If we assume that the black hole accretion is limited by the Eddington limit, we have high mass ratios, then a stable mass transfer can actually shrink the orbit by a few hundred solar radii, and this can also lead to the formation of such objects. So I already hinted that common envelope is one of the key uncertainties in this picture, but there are many others, as I show you in the list. I don't have the time to go through all of this, but I highlighted the ones that I actually investigated in this project. So first one is the first stable mass transfer. Second one is the mass transfer stability criteria. And the third one is the uncertainty at what stage the convective envelope develops. So we obviously expect that these uncertainties would have an effect on the emerging binary black hole population, but perhaps more importantly, it turns out that they also can change the dominant subchannel in the isolated binary formation channel. So in some cases, the stable can be the dominant channel. In some cases, the common envelope channel can be the dominant one, as I will explain later. A little about the methodology. I used a rapid population synthesis called SIBA. So basically, it's a Monte Carlo simulation where we sampled from some initial distribution. We ran it through the code, which gives us the evolution of massive binaries. And from this, we can obtain the population of the gravitational wave sources. In such rapid population synthesis codes, unfortunately, we have to use simplified physics, but currently this is the only way that we can simulate millions of binaries. With data simulations, it would not be possible. Okay, so in SIBA, these processes that I was looking at are parameterized by those parameters on the right. If you don't understand what they are at the moment, it's not a problem. Just want to give you an idea about the methodology. So we vary these parameters within reasonable intervals, mostly motivated by recent studies. And we come up with different models and different values for these parameters. We make combinations of them, and we have different model variations. And each model variation, we have actually 16 of them. We simulate them on a methodicity grid given below. So it would be very boring to go through all the 16 models. I try to just highlight the most important parts. So let's start with the uncertainties in the first table mass transfer. So sorry for the ugly drawing, but I hope you get the picture. As the primary field is in Roshmai, there will be probably an accretion disk, as a result of which the accretor star is going to spin up very fast. It turns out it can spin up to critical rotation very fast. And therefore, it's not so difficult to imagine that not all the material is actually accreted. Furthermore, donor can swell up so much that there could be matter leaving through the L2 point. So the two major uncertainties in this picture is that we don't know the fractional mass that's accreted. In SIBA, we characterize this by beta, which I'm going to refer to as a mass accretion efficiency. And the second one is the angular momentum loss from the system, which is characterized by gamma, which basically is the specific angular momentum loss from the system over the specific angular momentum of the binary. So these two parameters will determine the period after the first mass transfer, which I will now show is extremely important for the merger rate of the stable channel. So in order to illustrate this, I'm going to look at a bunch of sources which are just before the second mass transfer, which means that we're going to look at binaries which have an evolved star and a black hole. And in order to show the effect of gamma, I'm going to fix the black hole mass, and I'm going to show the range of donors. For the range of donors, a mass ratio orbiter separation space. So this is the plot that I'm going to show. On the y-axis, we get the separation log space. On the x-axis, we have the mass ratio. And we have two different models, gamma 2.5, gamma 1. If you're interested where these numbers come from, ask me later. I don't have time to go through it. I'm sorry. The first thing I'm showing is actually the maximum required separation that these binaries have to arrive at by the time they form black hole binaries if we want them to merge due to gravitations within Hubble time. So for this, we obviously need to assume what would be the black hole mass that the donor would form. For this, we assume that the mass transfer would happen at the hydrogen shell burning phase. So we are mostly interested in the source of stable channel. So this is a very typical way to estimate this. And just an example, I'm saying a 60 solar mass would form a 24.8 solar mass black hole at this given metallicity. The second line I'm showing here is that is an orbital separation that these binaries need to have at the onset of the second mass transfer if you want them to arrive to the black line. So here we are actually assuming that the change in orbit is due to a stable mass transfer. And here again, I'm just highlighting here the stable mass transfer can actually decrease the orbit significantly if we have a high mass ratio at the onset of the second mass transfer. But you need to keep in mind that there is a critical mass ratio above which the mass transfer will be unstable, but I will explain this later. So now let's just plot the distribution, the contours of the distribution that we get out for the two different gamma models from SIBA. And we can see that for the gamma 2.5 model, we get a portion of the population which would merge due to via the stable channel, whereas for the gamma 1 model, we don't have any such systems. So why does that happen? Obviously, these distributions are formed by gamma and beta. Gamma is actually turns out to be the more important one. And in order to demonstrate, I'm also going to plot the required initial separation that these binary need to have so that they arrive at the red line. So I need to point out that I made some simplifications here. Actually, I neglected the effect on the orbit from supernova, which might seem strange, but as long as we can trust the supernova prescription from prior 2012, at these mass regimes, the kick is not really significant. Okay, so the last line I promise I'm going to show is actually the initial separation that at which the initial primary would fill its Roche lobe when it's still a main sequence star. So all the systems which have an initial separation above this line would have their mass transfer, but the donor is no longer main sequence, and below that the donor would be main sequence. So what we see is that it's impossible to form stable channel gravitational wave sources if the required initial separation is such that the first mass transfer has to occur with the main sequence donor. This happens because those mass transfers have a very different outcome. For main sequence star, the core is not formed yet, and the mass transfer significantly can decrease the mass of the core. And by the second mass transfer, we would have low mass black holes. We would have therefore higher mass ratios, which would quite often occur in unstable mass transfers, and therefore they would not be able to form gravitational wave sources. So so I hope I convinced you that gamma can have a significant effect on the merger rate of the stable channel. But now I want to show, I want to quantify this, and I'm showing our results for these two different model variations on our astrophysical population. So I'm showing you the primary black hole mass histogram for different channels. I also, in the legend, I'm showing you the cosmic merger rate that was derived. But at the moment, just concentrate on the green histogram, which shows the stable channel sources. It clearly shows as gamma 2.5 is decreased to gamma 1, they practically disappear. And these predictions are not dependent on what we assume for the accretion efficiency. Okay, moving on, I want to tell how we assess the mass transfer stability criteria. So when we have mass transfer, then the Roche lobe is obviously changing because it's dependent on the mass ratio and the separation, which is changing due to mass transfer. Furthermore, the radius of the donor is also changing because it's trying to rearrange its equilibrium as the mass is donated. So then in order to assess the mass transfer stability criteria, we need to compare how these two radiuses change. And actually, if the Roche lobe radius is receding faster than the donor radius, then we have a runaway process, and therefore we would have a dynamically unstable mass transfer, which would lead to common envelope. So in order to assess this, we actually introduced these two parameters. The first one tells you how the Roche lobe changes with mass transfer. The second tells you how the radius donor changes with mass transfer on dynamical timescale. If zeta is larger than zeta add, we assume that the mass transfer will be dynamic unstable, and we will assume that we will have a common envelope. Okay, so in SIBA, we assume constant zetas per every evolutionary stellar evolutionary phase. And one of our model variations is to vary the zeta for giants with radiative donors based on the studies outlined there. And one important thing that I would like to mention is that actually it's very important to keep in mind that donors with convective envelopes have zetas, which are typically a small negative number. So basically it means when they donate some mass, they will actually expand a little bit. Therefore, they are ideal common envelope progenitors. So therefore, convective envelopes are very important. We need to know where they develop, but there's a lot of uncertainty regarding that. We used two different models, an older one from Ivanov and Tam, where they assumed that this happens at a constant effective temperature, and the recent one, which predicted that this would happen at a much cooler convective envelope, a much cooler effective temperature. So the latter one from Clanky et al. 2020, I'm going to refer as the cool convective prescription, and the former one, I'm going to refer to it as a hot convective prescription. So I'm going to straight jump to the plots about the simulated populations. I'm going to show histograms like this, 2D histograms. So basically here you here we show the masses of the merging binary black holes, and each column refers to a certain channel. So right column is CE channel, the left one is stable channel, and each row corresponds to a certain model variation. So on the upper one, you see the cool convective envelope prescription with low accretion efficiency. On the lower one is the same, but with high accretion efficiency. And the takeaway message is here, as long as we use the convective envelope prescription from Clanky, so the new one, and we have a low accretion efficiency, the common envelope actually cannot produce very massive gravitational wave sources. This is because for high masses, it turns out with this convective envelope prescription, they cannot really reach that, they never really develop convective envelopes. So the only way to form common envelope sources is through to a donor with radiative envelopes, but then you need high mass ratios. And because we have low accretion efficiency, the mass ratio at the second mass transfer will be limited. So we wonder what if we actually increase the mass accretion efficiency. We see that there are actually a few sources that are massive, but they're kind of negligible. And it turns out that there is another factor that narrows down the mass ratio distribution at the onset of the second mass transfer, and that is the LBV winds, which we assume that core helium burning stars experience. And there are some indications that these can be metallicity independent. However, if you use the hot convective envelope prescription, then obviously the assumed accretion efficiency does not matter, and there will be in either case a significant high mass component from the CE channel. Yes. However, I would like to point out that as long as the cosmic merger rate densities are concerned, in these model variations, the high mass regime is still dominated by the stable channel. However, that's not the case if we have gamma 1 and the hot convective envelope prescription. So I already showed you that gamma 1, the stable channel, is not viable, but it turns out that it actually increases the common envelope channel with convective donors. I would like to point out that yes, it's also possible, it also produces relatively high mass radial distributions, but the reason why actually the merger rate of the common envelope channel with convective envelope donor increases is because with gamma 1, after the first mass transfer, typically the orbit widens. And for this channel, that's actually beneficial because you want the first mass transfer to be stable. So you definitely don't want your donor to have convective envelope, but it's very easy to have unstable mass transfer. And if it widens, it's more likely by the second mass transfer, the donor will fill its Roche lobe at a later stage when it has already a convective envelope. So with the gamma 2.5 model, it doesn't really work out. So the last thing I point out is that changing the zeta, that is changing the mass transfer stability criteria, can either case increase significantly the merger rate of the stable channel, both in low accretion efficiency, both in high accretion efficiency models. However, when it comes to low accretion efficiency models, it only affects the lower mass regime of the emerging binary black hole population. This is something, unfortunately, I couldn't explain, but if you're interested, just ask me and I can show you why. And in this case, increasing the accretion efficiency can also widen the mass ratio distribution significantly. Yes, these are my conclusions. Thank you very much.
Thank you very much, Andres, for your talk. We have 3 minutes for questions. Scott, please.
So perhaps you said something about this, and I sort of looked at it. I was struck by the fact that you had very low metallicity. Assumed in all the plots where you showed a metallicity there. I'm just curious, to what extent does metallicity then? I mean, have you explored what the effect of that is on these conclusions as well?
Okay, so I showed some plots with very low metallicity, but we actually did a whole metallicity range starting from solar metallicity to extremely low metallicities. And yes, it has obviously a large effect on the merger rates. At low metallicity, typically stars are more compact. It can increase, for example, the merger rate of the stable channel. For the common envelope, typically we see a peak at a low metallicity, typically like below 5% of the solar metallicity. But at solar metallicities, because of the high stellar winds and because of these stars are not really compact, typical merger rates are quite low, at least according to all.
It was so low. I just wanted to make sure I understood. You're not necessarily requiring it to be, 10 to the minus 4, 10 to the minus 5, whatever that number you had was, but that was just what was used in those plots that you were showing.
Yeah, exactly. So as I said, we started from solar metallicity down to 1%, or yeah, it's very low. Yeah.
That clarifies things. Thank you.
Thank you very much. Other questions? I have a quick one, Andres. Is there any role for the magnetic field in the mass transfer, or is it unimportant dynamically?
Yeah, I mean, that's a very good question. I would expect that probably yes, but there are already so many complications to do a detailed hydrodynamical simulation of mass transfer that I think people are still trying to keep things relatively simple because it's already complicated. So maybe there are people looking at it, but I'm personally not aware.
Something for the future, maybe.
Yeah.
Fantastic. Thank you very much again for a very interesting talk.
Thank you. Thank you.
The next speaker is Professor Katerina Hatsuyano, and she will be speaking about constraining the neutron star equation of state with merger and post-merger signals.
Excellent. Can you see my slides?
Perfect. Thanks.
Okay. Okay, great. Thanks, everyone. And thanks to Andrew for organizing this session and staying up so late to chair it. I believe it's really late in Melbourne right now. So I'll be talking about neutron star observations with gravitational waves and how we can use them to constrain the neutron star equation of state. Hendrik sort of mentioned it in his talk, how GW1 can be used to do this. And in this talk, I'll be going into a lot more detail about how to do this. Perhaps unsurprisingly, GW1 is going to be the star of the show, but there are also other detections of gravitational waves from systems that probably involve neutron stars. So you've probably seen this gorgeous plot before of all the black holes and neutron stars, either electromagnetically or with gravitational waves. And what interests us is the low side here, those orange-ish dots that represent the neutron stars observed with gravitational waves. In this low side, of course, low mass side, the main thing that we are sort of certain about is that the 3.2 solar mass line. So everything above 3.2 solar masses is a black hole. Everything below 3.2 solar masses could be a neutron star, could be a black hole. Its nature is more uncertain. So in this low mass regime, we sort of have this observational gap between neutron stars and black holes, at least observed electromagnetically. Gravitational waves give us another way to probe what happens with all these systems. So the main motivation for this talk and for this line of study is what are those low mass, below 3.2 solar mass objects that we're seeing with gravitational waves, what are their properties, and ultimately what the equation of state for neutron stars is if these objects are indeed neutron stars. Okay, so like I said, the star of the show is of course GW1 and neutron star binaries. So this plot here basically summarizes what a neutron star binary looks like in gravitational waves. This is the amplitude as a function of frequency. You recognize the detector sensitivities there, the blue and the gray lines being the sensitivities back 4 years ago now, when 1708-17 was detected, and the design sensitivity, respectively, in blue and gray. And the other lines, the mostly yellowish, dominated by yellow line, show you the gravitational wave signal from two neutron stars merging, and the different lines here show you what different neutron star equations of state will do. So these are different models for the structure of neutron stars and the properties of neutron stars and how they result in different gravitational wave signals. So you will probably recognize the really long N spiral. That's where the two neutron stars are still fairly far apart. I'm talking about could be hundreds of kilometers and dozens of kilometers apart by this stage as they're slowly spiraling towards each other. This is When we say we are detecting gravitational waves from neutron star binaries, this is usually what we're talking about. This stage lasts for about 2 minutes, at least for 170817. So this is the vast majority of the signal we're observing. But you can see in this stage, the different colors all overlap with each other, which means that the different equations of state predict the same signal, which means that you cannot use that signal to study the equation of state. Later on, the neutron stars will get close together, and this is where the different equations of state start predicting signals that differ from each other. That's where things start getting interesting if you want to study the equation of state. And eventually, of course, there's no turning back. The neutron stars will collide, and they will keep. They will form a final remnant star that will keep emitting gravitational waves, which again depend on the equation of state. Okay, with this picture in mind, let's talk about how we can measure the equation of state and what we have done so far. So let's start from the late end spiral, because again, this is, as I will discuss a little bit more later, this is what we have been able to actually do today, while the rest for the post measure is more wish list for the future. Okay, so when you have two neutron stars that are still have not collided, they're still two separate objects, but they are like any other material object, they have a finite size, which means that they tidally interact with each other. This is the usual theory of tidal interactions. If you have a spherical object and put in an external field, what it will do, it will acquire a quadrupole moment. It will be tidally distorted. In a binary, you have two of those. So this thing happens twice. So each neutron star gets its tidal interaction. And the thing that causes the field that creates the quadrupole moment is, of course, the companion. If you have two neutron stars, one of them creates a tidal field, this epsilon ij quantity in this equation. And as a response, the other neutron star develops a quadrupole moment, the qij. The constant of proportionality is called the tidal deformability. And this is what we're actually going to be trying to measure, because the tidal deformability is directly encoded in the gravitational wave signal and depends on the equation of state, because the bigger a neutron star is, the more deformable it is and the larger this tidal parameter is going to be. So it depends on the equation of state, and also it affects the evolution of the system. Here's an example for how this happens. Here are two example gravitational wave plots in the time and the frequency domain. And these are neutron star binaries that have all their parameters the same, but the tidal interactions. And the different colors basically show you, as you change the tidal interactions in the system, what exactly happens in the signal. Perhaps it would be better if you focus on the bottom plot, where you can see that if the tidal deformability is 0, that usually we take to correspond to black holes. There's a little bit of a debate on exactly whether black holes have a 0 tidal interaction or not, but for all intents and purposes, let's say that 0 corresponds to black holes. That's the green line. And then as you increase this parameter, you go from neutron stars that are closer to black holes or more compact in the pink line to neutron stars that are less compact, more the blue line. And with your eyes, if you follow the peaks and the troughs of the gravitational wave, you'll see that what happens as you go from the black holes to more big fluffy neutron stars, as you go from the green to the pink to the blue, what happens is the evolution proceeds faster. Every peak is moved slightly lower frequency, slightly earlier times. This sort of makes sense. If your neutron star all of a sudden it's not spherical, it has a quadrupole moment, that causes additional emission of gravitational energy, so the system evolves faster. Okay, so we did that, of course, for 170817, and here is the result. There are a lot of things going on. Remember, you have two neutron stars, so you have two tidal parameters, lambda 1 and lambda 2. What you get is, can people hear me?
Yes, you cut out for maybe 10 seconds, Katerina.
Yeah, I got the message. The connection was unstable. I'm sorry. So let's try it again. So this is the measurement from 170817. And the conclusion seems to be that in the range of possibilities, those two neutron stars were more on the compact side. Because if you look at the posterior, these are concentrated to small values for the tidal parameters, which means less deformable stars, which means more compact stars. If you start going beyond 170817, of course, there is more. There is GW190425. GW190425 was very interesting on its own for various reasons, one of which is the following. If you look at the total mass of neutron star binaries that we know of, we know about 20 odd systems in the galaxy. These are the galactic neutron star binaries, and their total masses are at about 2.7 solar masses. This is the dashed line in this plot. 170817 fell squarely in this regime. Its total mass was about 2.7 solar masses. It was a poster child for galactic neutron star binaries. GW190425 does not fall into this nice picture. And that's where things start getting interesting, because the total mass of this system is more close to 3.2, 3.3 solar masses. The individual masses are around 1.8 solar mass, which is perfectly consistent with neutron stars. We've seen neutron stars that heavy in the galaxy, but we've never seen them in a binary around another neutron star. And GW190425 was the first such instance where we now know that 1.8 solar mass objects form binaries and merge, so they can be observed by LIGO. So this is both good and bad news when you're trying to understand the neutron star equation of state. The good news comes from what I just said, that now we know that massive neutron stars form binaries and merge, so we can study them. The problem is that if you try to actually study what happened in that system, everything is intrinsically more difficult, because the bigger a neutron star is, the more compact it is, so the harder it is to deform it. This statement has nothing to do with the equation of state. It has nothing to do with what the actual equation of state is. It's just a physics argument that the more compact a star, the harder to deform it. So the effect you're trying to measure is just intrinsically weaker. We, of course, try to do this, try to measure the tidal interactions in that system, but the outcome is that they were not, the measurement was not physically interesting. What I mean by that is in this plot, if you look at this plot, these lines here show you the upper limit we have placed on the tidal interactions, while this orange-ish line shows you where we expected tidal interactions to be. So this is the physically interesting region where we expected the effect we were looking for it to be. Our upper limit is much higher than where we expect the effect to be, so it's not an informative upper limit. Okay, so let's put everything together. Of course, gravitational waves are not the only thing that gives us information about neutron stars. We also know that two solar mass neutron stars exist, because we have seen some of those, again, not in binaries around other neutron stars, but we have seen them in binaries around white dwarfs, so we know that they exist. And we also have X-ray data about neutron star radii. And I'm not going to go into detail about how this measurement works, but if people are interested, please let me know. But if you put that data together, this is sort of the picture you're getting about the mass radius relation of neutron stars. If you start from a prior, that's the black in the analysis, and you take into account that we have seen heavy neutron stars, this is like 2 solar mass neutron stars, that means that the equation of state cannot be too soft. The pressure inside neutron stars cannot be too small, because if it were too small, it wouldn't be able to support 2 solar mass neutron stars. So these are heavy. So that pushes you from the black to the light blue. It pushes you to slightly higher radii. Gravitational waves have the opposite effect. Like I just discussed a few slides ago, gravitational waves tell you that the neutron stars were in the more compact side, where the radii were smaller. So that pushes you from the light blue to the green, pushes the radius down. Well, the X-ray data push you again in the opposite direction, where the radius cannot be too small based on those measurements. So that pushes you from the green to the blue. And at the end of the day, the blue is the final result. The blue shaded region is the final result for the radius measurement for neutron stars from that data. You can convert that to also the neutron star equation of state directly, and the equation of state of neutron stars is, of course, the pressure and the density. And this is given here on the y-axis, the pressure, on the x-axis, the density inside neutron stars. And again, the same combination of combination of colors gives you the same sort of data. If you start from the black, which is your prior, wrong arrow, I'm sorry for this. The radio data for the heavy pulsars push you up. Again, the pressure cannot be too low, so it pushes you from the black to the light blue. Gravitational waves push you down from the light blue to the green, and X-ray data push you again up because they put a lower limit on the radius or a lower limit on the pressure. The interesting thing to get from this plot is that we are now in a sort of situation where we don't just have some information and we're trying to see what that means for the equation of state, but we're also probing the equation of state and the neutron star structure in very different density regimes. If you notice exactly where each data set is more informative, the more heavy neutron stars, the 2 solar mass neutron stars, are more informative about what happens at the higher pressures inside, the higher densities inside neutron stars. Radius measurements and from X-rays and tidal measurements from gravitational waves are more informative about what happens at the more medium 1 to 2 times saturation densities. And while not shown on this plot, actually, if you consider something like nuclear theory and terrestrial experiments here in terrestrial laboratories, those would give you information about the slightly even lower densities below the nuclear saturation density. Okay, so something that I will eventually get to be an issue for us for gravitational waves, and something that every time we get excited about what we can do with gravitational waves, we have to keep in mind, is the issue of waveform systematics. And I'm not going to go into too much detail other than to just say about waveform systematics that currently we believe they're under control because we have different models to analyze the data and we're checking. So the plot here shows you results for GW17, 0817 with different waveform models, and they're all consistent. But moving forward, once the detectors get better, or once you get more signals, you will actually start seeing problems, waveform systematic issues. So the plots here show you simulated data because we don't have the best detectors, the best detectors that can possibly be just yet. Our instrument scientists are working on this. But once you have those detectors in a few years, if you see a signal like this, then you will not be able to measure tidal effects in a way that is not dominated by systematic uncertainties. And the plots here, the different colors, show you what you would get from such a system. That is not reason to panic because there are a lot of people who are very actively at work to improve all those models. And even since 2018, where this plot was made in the study that is cited at the bottom, the waveforms have already been improved. So they will. We're optimistic that by the time actually we get a design sensitivity in a few years, then waveform models are also going to have improved. But if today, with today's waveform models, or for the ones we had in 2017, we saw a signal that was 3 times as loud as GW17 or 817, we would indeed be in trouble. Okay, I'm going to skip that in the interest of time and talk a little bit about the post-merger as well. So this is the final part of the signal. Eventually, as the 2 neutron stars collide, they will mash together to form one final remnant that will keep emitting gravitational waves. And roughly speaking, there are 3 possible fates for this remnant if you have a neutron star merger. On the right side here, one possible outcome is that the merger remnant is so massive that it collapses immediately to a black hole. There's nothing that can support it against gravitational collapse. In this case, this looks like a normal binary black hole signal. The final black hole will keep emitting gravitational waves in a ring down type signal. But the frequency of that signal is about 6,000 hertz, which is absolutely prohibitive for us to either our detectors or our analysis. On the opposite side, the opposite part of the plot, on the right-hand side, the other possibility is that actually it does not collapse. It survives as a neutron star either for a very long time or even indefinitely, supported by rotation. If the mass is low enough, this can happen. In this case, because it's a neutron star that survives indefinitely, you have, or for a long time, you have a long duration signal that you can go and search for. And indeed, there are a lot of searches for those signals, including after 1708-17, none was detected. And I believe there were talks on other days about these types of analysis as well. What I will talk about a little bit more is the in-between region, where you have a neutron star that survives for a little bit. And when I say a little bit, I mean milliseconds of tens of milliseconds before it loses its support against collapse and just collapses into a black hole. The gravitational wave signal emitted in this stage is going to be short duration because, like I said, the neutron star survives for tens of milliseconds. And the frequency at which it's coming is at a few thousand hertz, which is on the high side. The detectors lose sensitivity at high frequencies, but 2,000 to 3,000 to 4,000 hertz is something that we can work with. 6,000 hertz, which is the binary black, the black hole ring down, is completely prohibitive. But 2,000 to 3,000 hertz we can work with. Okay, in this case, of course, any sort of attempt to analytically understand what's going on in the system is going to fail. This is a very complicated, highly nonlinear, quickly evolving system. So you have to do numerical activity simulations. And here's an example of such a simulation of what the signal looks like. In the middle, you'll see the signal in the time frequency. So time frequency decomposition, where the colors are darker. This is where most of the power comes from. And the top is projecting the time domain. You see how complicated the signal looks like. And on the right is the signal and frequency domain. And the main interesting thing about such a signal, at least from a data analysis perspective, when you try to extract it, is that it looks like most of the power comes from a single frequency component. Not exactly, but to a pretty good approximation, this seems to be the case. And that frequency component seems to also depend on the equation of state. If I show you two simulations here, pull up two simulations of neutron stars merging, you see the end stages and the final remnant. The ones on the right are smaller, more compact, and are rotating faster than, the ones on the left are smaller, more compact, rotating faster. The ones on the right that's a more diffuse remnant and it's rotating slower. That means that the more compact the star, the higher the density, the higher the frequency at which it emits radiation in this stage. So exactly where that frequency is and the location of that peak depends on the equation of state. And we can, if we measure it, we can say something about the equation of state. All the possible types of signals from neutron star remnants were searched for 1708-17. The bottom right of this slide, I have a few references about the short duration signal and the long duration signal. But the plot here shows you what happens for the short duration signal, a search for the short duration signal. And this is on the y-axis, the energy as a function of frequency. So how much energy you can extract at this frequency. And the outcome is that none of these analyses found any post-merger signal. You go from, what happened is you start with some prior upper limit, that's the, pinkish color, and you push down to a posterior upper limit because you didn't detect the signal, which is the blue upper limit. In reality, though, this is not too surprising. The fact that we didn't detect it doesn't really mean much. The reason is that we didn't expect to detect it, even if such a signal was there. The lines, the various colored lines, show you what you expected roughly the signal to look like from different simulations and different equations of state. So our upper limits are not yet at the stage where a potential signal would be. So the fact that we didn't observe a signal does not mean that it was not there. But going forward, we can detect it. Going forward, the detectors are going to be improving in sensitivity. They've already improved in sensitivity quite a lot since 2017. They will keep improving in sensitivity. And I'm going to show you here an animation of what happens if you have a signal that you observe in increasing detector sensitivity. So as the dashed line in the bottom panel is the detector sensitivity. So as that line comes down, that means your detector is improving in sensitivity. And the black line, solid line, is the signal, the simulated signal that you put in. And as you know, as the detector sensitivity improves, the dashed line goes down. All of a sudden, you start extracting the signal from the noise and measuring its various frequency components. So something like a detector 2 to 3 times better than advanced LIGO could do it, could detect such a signal. I know that a detector 3 times better than the design sensitivity sounds scary, but this is within reach of proposed and funded instruments. So it can happen in a few years. And I'm going to skip this and just show that in the meantime, besides just improvements in the detector sensitivity, we are also going to have improvements in our analysis. So I sort of presented this, discussed the pre-merger and the post-merger separately, but ideally, we want to actually start combining them. We want to have a full analysis that can handle the full signal. And there's some preliminary results from University of Southampton grad student Marcella Weingarten, where that shows you the analysis of the full GW170817 signal, both the pre-merger and the post-merger. And you can see the nice pre-merger single line above the noise of the detectors that you measure. The post-merger still remains undetected. It's very wide and undetected, consistent with 0. But improved analysis like that could decrease the time to detection by a bit. Okay. I was going to talk a little bit about neutron star black holes that are the new kid on the block these days with new detections, but I think I've run out of time. So if people are interested, I can answer questions, but for now, I will just leave you with my final slide and take questions.
Thank you very much, Katerina. That talk raises so many interesting questions. I don't know where to start, but I'm just going to hand it over to the audience. So we've got 4 minutes for questions. Scott, please.
So, Katerina, you anticipated something I was going to ask about, which was to ask specifically about the kinds of future instruments you were looking at. But one other question sort of came up is people have talked about advanced detector topologies that would enable it to sort of make a narrow banded kind of configuration. So you can imagine getting really good sensitivity in a relatively narrow band. Is that something that people have considered for going after, in particular, some of this post-merger signal? Do you know if that's sort of that idea is still in play?
Yeah. Let me pull up perhaps this plot. Yes, so these ideas are still in play. They're sort of considered parallel to squeezing, but also improves the high frequency sensitivity. There are 2 issues here, though. First, from what I understand from talking to people like Matt Evans, who's an expert in this, is that it's technically challenging to get this to work. And the second issue that is more related perhaps to things that I can answer is that the frequency is constant for a given mass. So if you are expecting to see a total of like 3 neutron star binaries per year, and you ask me to pick a frequency to tune your detector out, I cannot give you this because I don't know the mass, even if I knew the equation of state. But if you go to something like 3rd generation detectors, where you expect to see 100,000 of those, I would say, sure, tune it to get it better. If we lose one system because it was too low mass and didn't merge within your tuning, sure, we'll wait for the next one. But don't do it while we're only seeing like a handful of events.
Good, thank you.
Thank you very much. The next question from Hendrik, please.
I apologize if this question comes off as naive or way off base. A colleague of mine always goes on about resonance effects happening, and they could trigger then a break of the crust and then an electromagnetic counterpart, which is, of course, why you had a conversation with me. But my question is this something that actually then would be visible also in the gravitational wave signal, resonance effects or anything like that? Or did you actually discuss those and did I just miss them?
Yeah, no, that's a good question. That's a lot of people are thinking about this. There are a lot of kinds of resonances that you can have. You can have resonances that are going to really affect the signal, and you can have resonances that don't couple so strongly to it. I think the kind of thing that you're discussing with the crust breaking, right? I think this is what you're discussing. The crust breaks at the very late stages, and there's a precursor. In that case, the signal won't be affected as much because the crust breaks, but the gravitational wave, you can think about what caused the gravitational wave emission, it's still the motion of the two cores that are going around each other. Unless you have something really disrupting the entire neutron star, the signal won't be affected as much about just the crust shattering. You can have other resonances that can hit the neutron stars and can start draining energy from the orbit. But I think these are different kinds of resonances. But all those things are things people are looking at. But you can have things like F mode and G mode resonances as well.
Yeah. Okay. Yeah. Okay. Thanks a lot.
Mm-hmm. Mm-hmm.
Thank you very much. We've got like 30 seconds, but Alexander, do you want to ask your question very quickly, please?
Yeah, sure, real quick. With Marcella Wingarden's work, is it like a combination unmodeled and modeled search? Or what's like the nature of it?
Yeah, that's exactly right. I didn't want to go into too much detail, but the pre-merger we have models for. We have our very nice templates thanks to tons of work from people, and you can use those directly. And for the post-merger, you don't have any models that can accurately produce any kind of an R simulation. So we use an unmodeled analysis. But the thing is, if you do this together, you can coherently take you through merger and use some information from the pre-merger to help you find the post-merger better. Rather than consider it as a standalone signal, you know that there is a continuation in between the pre-merger and the post-merger, and you leverage that.
Okay, cool. Thank you.
Mm-hmm.
Thank you very much. Katerina, thank you. That was a fascinating talk.
Thank you.
And again, if the audience has more questions, don't hesitate to pop them into the chat. And I'm sure Professor Katsuano will be glad to answer them. The next speaker is Fabian Gittens, and he will be telling us about neutron star mountains. Fabian.
Cool, thank you, Andrew. I'm just going to share my screen now. Let me just full screen this. Brilliant. Hopefully you can all see that.
Perfect.
Brilliant. Okay, thank you. I'll start now. Hello, everyone. My name is Fabian Gittens. I should say good afternoon, because that's where I am right now. I suspect many of you, it's morning and evening, because this really is very much a global conference. First off, I'd like to thank the organisers for giving me the opportunity to speak about some of my work today. What I'll be talking to you today about is how we model neutron star mountains, which is a popular problem for gravitational wave physics. What I'll be discussing is essentially a summary of two papers that I've had the privilege of being involved with alongside my collaborators Niels Anderson and Ian Jones, both at the University of Southampton with me. This first paper was published earlier this year, is on the Newtonian aspect of the problem, and then more recently we've pushed this to the archive, which is a calculation for general relativity. So if you're interested, do check out those references for more information. You know, I find that we often take the era of gravitational wave astronomy for granted. You know, I remember back in 2017, I just started my PhD in September, and we were hit with this incredible multi-messenger event, GW1 which actually many people have talked about at this conference, including Professor Katsuano in the previous talk. I'm just showing you this plot here, which we did see in the previous talk, which I think nicely illustrates some of the really exciting things we'll be able to do for neutron star physics with further detections. What you see here is a posterior probability distribution of the two tidal deformabilities of the two components. And what these lines indicate are confidence intervals of different equations of state. And what you can see is the different colors correspond to different assumptions about the spin. But what you can see is essentially, even with one detection, we've been able to reject some of these very, very stiff equations of state just from the gravitational wave signal. There's no electromagnetic data in this. And I think that's a really exciting story. And the hope is with more detectors, we'll be able to get smaller and smaller sort of regions and get a better handle on the elusive neutron star equation of state. What I'll be talking today about will be a slightly different problem to the binary problem. We'll be looking at rotating isolated neutron stars that host non-axially symmetric deformations, which we rather humorously call mountains, even though they're quite small, of the order of millimeters to centimeters. That'll be the subject of some of this talk. There has been quite a substantial effort looking for these mountains in the gravitational wave data. And even though they haven't been detected, that does give us information about the upper limits on the size of the involved deformations for the neutron stars that have been targeted. And in a complementary approach over the past 2 decades, starting with this paper by Roshmai, Cutler, and Bilston back in the year 2000, there's been an effort to understand theoretically what the largest mountain a neutron star crust can support before it begins to fracture. And the hope is with these complementary approaches, we'll get a better handle on some of the physics. In this slide, I'm just going to just try to introduce some of the language I'm going to be using. We describe mountains in terms of the multiple moments. This helps us get a handle on the size of the deformations. Particularly, we tend to encounter these multiple moments by looking at the exterior gravitational potential of a source. The way we'll be defining them for this talk will be the difference of a non-spherical body with its spherical one, and generally that will be assumed to be perturbative, so we can work within the linear perturbation regime. In the Newtonian limit, we expand the gravitational potential using spherical harmonic modes, and then for the individual modes, we can identify the multipole for that LM mode based on how it falls off with the radius, and this is in the exterior of the star. And this enables us to write the multipole moment as an integral over the mass density perturbation across the star. For gravitational wave emission, as I'm sure many of you are aware, the dominant multipole is the quadrupole moment. That's the L equals M equals 2 mode. And for this work, indeed has been done in previous work, we'll assume all our perturbations are in this single harmonic mode. In order to introduce a variety of stellar models, we'll be characterizing them using the static Euler equation. This is just the equation of a force balance, I guess, in the star. And what you see here is you see the derivative of the fluid pressure, which for a completely fluid star is balanced by the inward acting gravitational force. Our neutron stars will host crusts, so at some region we'll need to take into account the shear stresses. And then there's a piece here at the end, which I'll talk a bit more about later, which is essentially a deforming force, which introduces the non-sphericity into the problem. This is all done in Newtonian, but we have generalized this work to relativity, but I find the physics easy to see in Newtonian gravity. So how has the problem been tackled in the past? Well, hopefully this illustration here on the left will help us understand. What I have here is a spherical star. It's a reference star. It's because we know how to build mathematically perfect fluid spherical stars. But in reality, neutron stars are rarely ever going to be spherical. They're often going to have some form of non-sphericity. You imagine that a neutron star is born from a supernova. It retains some of the angular momentum of the progenitor, and so it'll be spinning quite rapidly. It'll be very hot, so it'll be its crust will be molten, so it'll be a completely fluid star, and it will probably look a little something like this. And we can build this mathematically by imagining we start with star S and we give it some sort of centrifugal force due to rotation. And then we imagine that the star, as it cools down, it starts to solidify its crust. And so we end up with a star here, A tilde, which is formally the same shape as A, but it has a non-zero shear modulus where the crust is developed, and the crust is relaxed in this configuration. And then you imagine you take away the force that gives us star A, such that now the star changes shape, and the crust then gets strained as the shape changes because it's relaxed in this configuration. It wants to go back to this configuration. And this we're going to call star B. And this is the star that often we're talking about when we say a star with a mountain. It is a star that is self-consistently supported solely by the shear stresses due to this sort of change of shape. And perturbatively, we can describe it using equation 1, which is just the difference between stars B and S. And here you see that you can describe this solely using the shear stresses. However, there's a few things to note about this. One is that actually imposing boundary conditions can be a bit difficult written in this form. One has to be particularly careful when going from the fluid regions of the star to the elastic regions in satisfying the traction conditions, which must be continuous across an interface. Additionally, it looks like the force that actually plays quite a big role in describing the star's initial shape is hidden in this calculation. It doesn't appear at all in equation 1. And this force is some sort of proxy for the evolutionary history of the star. The star might have undergone a series of crust quakes or glitches which changed its shape subtly. And this force is meant to do the heavy lifting there. So to this end, to deal with, I guess, these issues, we've introduced a new scheme, which I'll describe on this slide here. So we've met star S and star A in the previous slide. We introduce a new star, star S tilde, which is a spherical star, has the same shape as S, but again has a shear modulus towards the surface, and it's relaxed in the shape. We apply the same force as above to give it a non-spherical shape, and we end up with star C. Now, one could imagine that if we subtract these two stars, we almost, in a perturbative sense, we get rid of this force, and we end up with equation 2. And equation 2 is very similar to what we saw in the previous slide. In fact, we were able to show at the linear perturbation level in our first paper that actually these are formally the same calculation. So one can obtain star B while having full control of the boundary conditions, but while having full control of whatever force gives you the star shape, you can build stars A and C in this fashion and subtract them from one another. So that's kind of neat. Right. I'm now going to talk a bit about, I suppose, our results. What I've been describing up to now is been done in toning gravity. Like I said, this is partly because I think the physics is easier to see and the equations are less long and less non-linear. So we were able to explore using fully relativistic neutron star models by changing the force for a few. For a few models, basically. And in order to make connection with the sort of maximum mountain problem, that is an open, a question of interest for those working in gravitational waves, we ramped up the amplitude of the force for each of the examples we considered until the crust began to break. And this generally happened towards the weaker outer regions of the crust. And this gave us the maximum mountain that each star could support for a given force. And this plot here illustrates quite nicely a few different deforming forces and the dependence of the mass quadrupole moment on the masses. Here I'm showing the ellipticity. This is a dimensionless description of the deformation. And you can see actually the numbers are very, very small. These deformations, although they span quite a range because of the dependence on the force, we're not getting much bigger than 10 to the minus 8, which is about a factor of a few to an order of magnitude smaller than previous estimates. And this, to kind of give an idea of why this is because previous estimates essentially ensured that the entire crust was maximally strained, whereas because we're worried about boundary conditions, you don't quite have the flexibility to do that if you want the traction to be continuous. So we were also able to look at the dependence on the equation of state. We used a couple of sort of generated models from chiral effective field theory that used a speed of sound parameterization. All of these models obeyed causality, and they're shown in these two plots here. On the right, I'm just showing you the mass radius curve for a number of these models. These two horizontal lines indicate the sort of recent nicer results. Their earlier one, I think, back in 2019, and the more recent one for the higher mass system. And I'm shading sort of the allowed region that sort of satisfy these constraints. So these kind of equations of state are broadly in the right region. I don't know how well you can see this. On the left, what I'm showing you is translating that kind of shaded region to the quadrupole sort of diagram, and you can see that across these equations of state that there's about an order of magnitude difference. So there's quite a lot to do here, really. Brilliant. I'm going to spend the last few minutes just sort of summarizing, and then perhaps we'll open some questions. So the work I've described has essentially introduced a new scheme in order to calculate neutron star mountains. The reason we needed to do this was to address some problems with boundary conditions that previous efforts had. However, in order to do this, we needed to introduce the deforming force that was previously hidden in the calculations. In reality, this force is going to depend on the formation history of the star. Things like crust quakes are going to change the star. Glitches are going to make a difference. Spin up, spin down, accretion, for example, if there's a binary companion. And this is just a whole load of unknowns. And in reality, in order to make progress, we're really going to need some evolutionary calculations in order to better motivate what this deforming force needs to look like. We've seen, perhaps unsurprisingly, that the neutron star equation of state plays quite an important role in supporting the mountains. In particular, and I didn't go into too much detail about this, it's the shear modulus of the crust that has a significant impact on how large the crust can be. In fact, it's the size of the mountains are linear in how strong the crust is. And then kind of as a final point, kind of, which is quite speculative, the work we've done has been assuming sort of the crust is an elastic solid. That's a linear relationship between the stress and strain, and then up to a certain point called the breaking strain, the crust breaks and all the strain is released. However, a lot of materials exhibit plastic deformation. And in plastic deformation, what you reach sort of the usual breaking point, but actually not all the strain is released at that point. Some of the strain remains in the star. And so perhaps it's plausible that the neutron star crust exhibits some plastic deformation where you could perhaps force incrementally different parts of the crust closer and closer above the breaking strain and build larger mountains. Again, this is quite speculative, but perhaps there's some work to be done here. I'm going to thank you very much for your time. I'm going to quickly flash my references for anyone that wants to follow up on some of the things that I've shown here, and call it there.
Thank you very much, Fabian. A very interesting talk. Okay, we have 4 minutes for questions for Fabian. While people are thinking, I've got a quick one. When you do the cracking problem, Fabian, do you use a particular kind of breaking criterion which is somehow related to microphysics, or is it phenomenological? How do you go about that step?
Yeah, thank you for your question, Andrew. So the criterion that we use, if you wanted to Google it or search the literature, is called the von Mises criterion. This was first introduced actually in the Urshaminski and Cutler and Bilston paper. I believe it comes from engineering. Essentially what you do is you look at the strain tensor, you contract over the indices, and that gives you a scalar quantity, and then you find kind of that corresponds to sort of the von Mises strain. And then I think there's been quite a lot of calculations done using like I said, microphysics, like by people like Chuck Horowitz and Kadow, looking at what that might reasonably be for neutron star material, and that gives and that's kind of the maximum breaking strain. So once the scale of quantity that we calculate is bigger or equal to that breaking strain, then we say the crust is broken at that point.
Understood. Okay, yeah, no, that's clear. And do you have a sense for how, what sort of error to order of magnitude do you get by doing it in a Newtonian way rather than with full GR?
So in terms of our mountains, I'll just go back a slide or two. This is probably the most informative block. So yeah, the ellipticity changes by quite a lot, actually, Andrew. I think roughly we saw suppression, so that as in the ellipticities was smaller by about an order of magnitude in going from the Newtonian to relativistic calculation. I can say a few words about why that is. One of them is there just seems to be a property of space-time that people have seen in tidal calculations in Newtonian relativity, where the stiffness of the space-time is such that you see a suppression in, say, the tidal log number. The second reason, I think, is partly because in the Newtonian calculation we were a bit lazy with our equation of state for the crust, and the more realistic crust equation of state was fractionally weaker than the Newtonian one, so that played a role as well.
Fantastic, thanks. Sorry, I didn't mean to monopolize the questions. Are there any questions from other members of the audience? Aaron, quickly.
Hi, I have a quick question. I'm sorry if it's a little naive. I was wondering, I had seen your paper earlier this year on the relativistic solution that you propose, and I was wondering about this discrepancy between the criterion of the breaking strain across the entire surface versus at one point, and how that leads to inferred mountain sizes that are different. And I was wondering if you could provide some more intuition for that point.
Yeah, Aaron. Sorry, could you repeat your question? You said something about breaking strain across surfaces.
Yeah, sorry. I had remembered when I was reading your paper earlier this year, there had been a mention that your results for your mountains being substantially smaller than earlier results in the literature was because you're calculating your criteria for the breaking strain at a single point versus other researchers who have done it across the entire surface of the neutron star. And I was wondering if you had any way of providing more intuition about how that translates directly into order of magnitude reductions in the mountain size.
Yeah, sure thing, Aaron. I'll say it quickly because I'm sure Andrew wants to bring us on to the next speaker. So the quick answer is in the previous calculations, ensuring the entire crust was maximally strained, actually violated boundary conditions. In particular, it violated what are called the traction conditions, which is a statement that the traction vector, which must be continuous across all interfaces throughout the star, was violated. So what they did is they looked at the strain field of the star, and they set that at a value. They said this is the value we want it to be. Whereas it seems pretty clear from looking at the equations that you can't do that, because the star, it's not a physical solution to the equations. I hope that answers the question.
Yeah, it does. I'll follow up in the chat. Thank you.
Thank you very much, everybody. Thank you, Fabian, for a great talk. The next speaker in the session is Professor Scott Hughes, and he will speak about the phenomenology of late-stage binary black hole gravitational waves.
All right, so looks like I've unmuted myself successfully. It's a good sign. All right, thank you, Andrew, for staying up ridiculously late in your time zone to run the session. A pleasure to be giving this talk here. I've not done too many of these virtual talks, but I'm actually in my office today, and so that's a step towards actually doing this in 3 dimensions with humans, but I'm looking forward to soon. So the goal of today's talk, what I want to tell you about is some work I've done with some junior colleagues, who I will name in just a moment, to understand how we can use black hole perturbation theory as a way to understand what kind of waveform we might get that terminates the end of the binary black hole waveform. There's a couple of motivations for this. I'll get into in a little while. The shorter version of my talk, which I really should have submitted this as the title, is the title of one of our papers that associate this, which is really all about learning about the properties of the binary from the ring down waveform that terminates the end of the binary black hole waves. So this is work that is based on things I have done with Anu Japte, who is a former MIT undergraduate, now he's a graduate student in string theory at the University of Chicago, Halston Lim, one of my current graduate students, and my longtime collaborator, Gaurav Khanna. So a quick outline of where we're going in case I need to sort of speed through things a little bit towards the end. I want to talk a little bit about why we are using perturbation theory as a tool for exploring the properties of gravitational waves from binaries. Okay, but strictly speaking, only applies to large mass ratio binaries. But I'm going to argue that we can learn things from this that are useful more broadly than that. To tell you a little bit about the method we use, and then perhaps most interestingly, survey what we find in the results. In particular, describe the way in which I'm going to kind of argue that there is potentially, especially as we get to more sensitive detectors, a lot of interesting structure in the ring down modes, which for various reasons, I think it's going to be important for us to model more carefully than perhaps it's being done at the moment. And I've been working with some colleagues on building that into other things. There are some limitations to our analysis, particularly because I use black hole perturbation theory as my tool. But there are some lessons from that I believe carry over to more general cases. So I have to remark, so when a Fabian said in his thing, many of us take for granted this era of detections of gravitational waves. I started my PhD in 1993, and so I've been thinking about this since long before there were any measurements of gravitational waves. So I will never take this kind of waveform for granted. There is, going back to some work that was, it was timely when I was beginning my PhD. We have this picture of what the binary black hole waveform was kind of going to look like, which told us that in the early part of the in spiral, we're going to have this slowly evolving orbit whose character would depend on and thus encode the nature of the binary and the members of the binary when those members are widely separated. And then it would terminate at the end with a set of ring down waves, which tell us essentially about the properties of the remnant when those two black holes come together. And you only have a single black hole that settles down to the Kerr solution. This traditional picture is certainly not wrong, but I'm going to argue there's a little bit more to it than this. Okay, we know that the ring down waves have a functional form that's essentially it's a damped sinusoid. And the frequency and damping time associated with those sinusoids are entirely set by the mass and the spin of the remnant black hole. And here's some wonderful plots from a paper by Berti, Cardoso, and Stanietz that shows the way in which the frequency and the quality factor, which is simply related to the damping time, are controlled by the black hole's mass and spin. So indeed, those two numbers, the damping time and the frequency, are entirely set by the properties of that remnant black hole. But there's more structure to these plots than just the shape of those curves. In particular, you'll note there are a large number of modes that are present here. And so the question which kind of motivated us to begin thinking about this is, which of these different LM ring down modes are actually excited? Which modes are going to be the strong ones that appear in the binary black hole waveform? And what we are finding, and this is not too surprising, is that the excitation of these modes depends on the late merger geometry. So we can imagine that there is some kind of a mapping between the excitation of different LM modes as a function of the binary black hole geometry. If we understand that mapping, then when we measure the modes, we measure the binary's geometry. So this is sort of an independent way to get information about the properties just from the late ring down thing. This gives us more information about the properties of the binary that produced this signal. As I was thinking about this, I was thinking through some of the talks in the session, I think it's worth also bearing in mind things related to some warnings we've had about systematic effects in your waveform. If there are other modes that are present in the waveform but are not being included in your model, those could be mistaken for structure beyond general relativity. So as we start thinking about using these waveforms as tools for testing the nature of gravity, we need to make very complete waveforms. We need our models to include all this kind of structure in order to avoid introducing systematic errors from overlooked effects, such as I'm going to talk about here. So our goal would be to explore this mapping. Obviously, what we'd like to do is to explore it over the entire parameter space of binary black hole mergers. That must be done with numerical relativity, which would be a very expensive undertaking. We are taking a first step on the analysis my collaborators and I have done by looking at this in the large mass ratio limit, which allows us to treat a binary as the exact space-time of a Kerr black hole perturbed by an orbiting body. And what this does, it allows us to quickly explore how the binary geometry determines the excitation of the different modes and thereby sets the final ring down waves. So let me tell you just a few technical details about how we actually do this. So when we're working with black hole perturbation theory, we don't need to integrate the full Einstein equations of general relativity. The problem just reduces to solving Tucholsky's equations governing perturbations to a black hole. So this mess I have on the screen here is the partial differential equation that governs a field psi. So for those of you who are fluent in the Newman-Penrose formalism, this is essentially psi4. This is a field that describes radiation far from the system when we set the parameter s, which is a spin weight, to -2. The factor t, which is on the right-hand side of this thing, describes whatever is the source of your perturbation. It should be emphasized that this is a linear equation. Okay, so for a binary, the t that I'm going to get is just proportional to the mass of the perturbing body. This is a good setup for studying binary dynamics with a large mass ratio, but it means I'm going to be making errors when I try to extrapolate this to different mass ratios, or if I take the mass ratio too close to unity, for example. It's also worth emphasizing that when t equals 0, okay, I have an unsourced wave equation in that case. The solutions of this equation are the quasi-normal modes that describe ring down. So this, in fact, is how the kind of ring down modes that paper by Berti, Cardoso, and Staranets, that's what they use in order to develop those solutions. They essentially study this equation with the right-hand side equal to 0. Hold that thought in mind. We'll return to this point in a moment. So our focus, using the fact that we now have a well-developed technology for solving this, given a particular source, what we're going to do is treat this equation as a 2 + 1 dimensional partial differential equation. I'm going to treat my fields as essentially depending on time. There's some technical details there. We can talk about that offline. Radius and polar angle. Because of actisymmetry, I can actually take out my phi dependence. That simplifies things. And so I compute this field given a prescribed source. And so here's a couple key references that describe how we do this. The source that we are going to use is that of a small body which inspirals due to gravitational wave emission sometime around the last stable orbit. So during that inspiral, I can think of this body as moving through a sequence of exact geodesic black hole orbits. It undergoes a transition that carries it into a regime that sort of goes beyond where it passes through the last stable orbit. And then it terminates in a trajectory that is well approximated by a plunging geodesic that carries it into the larger black hole. So this plot I am showing you here describes the world line that this thing follows, the radius versus time of a small body as it plunges into a black hole with a spin of 0.5. Okay, and so there's a couple parameters that tell me where the transition starts, where it ends. The key thing I want to emphasize, there's a lot of sort of dirt in here that I don't have time to get into, but you can find the paper that the undergraduate and I wrote together lays out all of this, and it both generalizes, and it turns out to actually fix a couple details that are in some older work that inspired us by Amos Ori and Kip Thorne. I want to make a few comments about this trajectory. So in terms of the physics, one of the most important is that when you look at the source of our wave equation, it's proportional to the stress energy tensor of a body moving in a black hole spacetime. And that is the form that I've written down here. The key thing which I want to emphasize is note that this stress energy tensor is proportional to 1 divided by the factor which converts coordinate time very far from my black hole to proper time local to the orbit. It's kind of a redshift factor. And as the small body approaches the event horizon, that factor diverges. Again, this is the well-known fact. This goes back to the whole frozen star viewpoint, that an object moving near a black hole appears to freeze to the horizon as seen by distant observers. When this happens, the source term of my wave equation actually redshifts away. It goes to 0. And so the wave equation automatically converts into its homogeneous form with no source. This guarantees that the waveform actually ends in ring down modes and does so in a way that is phase coherent with all of the in-spiral signal that came before it. The other thing is sort of a criticism of our approach is that the way that we govern this sort of transition from a slow in-spiral to an eventual plunge, unfortunately has a few free parameters in it that we do not have very good control over. Our formalism sort of tells us approximately where they may be, but there's a little bit of freedom to choose them. And freedom in a problem like this is not the best thing. We wish the physics told us how to control them a little bit better. it turns out that the choice of when to start this transition has essentially no effect on these trajectories that we produce. So that's nice. However, the way in which the world lines end does depend on, that does have an effect on the world lines that we produce. I'm going to describe a little bit later. These turn out to be harmless, provided they're harmless for us for understanding the mode excitation. So if we're learning about the gravitational waves, this doesn't really bother me. It is, however, just as a matter of principle, irksome. And so it would be great to remove this need to make choice. And I want to make an advertisement to a beautiful paper by Geoffrey Conqueret and his student Küchler, which shows a way to actually make a self-consistent in spiral and plunge, at least in the equatorial limit. They have not generalized their analysis to arbitrary orbital inclination yet, and we really want to look at the case of spin and orbit highly misaligned from one another. But this is a really important step in that direction. Finally, one of the things that we discovered in doing this is that having a good parameterization really cleans up the way we interpret our results. So just to give you a bit of a catalog of how we're going to look at things, the key parameters for us are a black hole spin. Okay, so we're going to choose our larger member of our body to have a particular, it's going to be a curved black hole, it's going to have a particular spin parameter. The orbit's inclination angle. So this tells us about the spin orbit misalignment. So when I is 0, it is a prograde equatorial orbit. When it's 180 degrees, it's a retrograde equatorial orbit. And then there's 180 degrees in between those two. That angle turns out to be approximately constant over an in-spiral. And by approximately, I mean it changes by less than about 1/10 of a degree over an in-spiral. So we're just going to treat it as a constant in this discussion. Interestingly, we then found that the best, there's a very important parameter that is essentially an accidental phase. And this is, we call this theta fin. It describes the angle at which the small body crosses into the event horizon of the larger black hole. The reason why this is important is that every one of our in-spirals basically belongs to a family of in-spirals that have identical starting energy and identical angular momenta, but they can cross the horizon at different angles depending upon a value of a starting phase, essentially. So to sort of illustrate this, here's 2 examples of some in-spirals I'm going to talk a little bit more about in my remaining few minutes. So on the left, this is an equatorial case. The orbit is completely confined to the equatorial plane. The small body crosses into the event horizon at theta equals 9 degrees. There is no freedom here. On the right, this is a case that was highly inclined. For the phases that we chose here, this guy happened to cross the event horizon at 52 degrees, but it could have crossed anywhere in the range 30 degrees to 150 degrees. We found that the value of this theta fin has a really important impact on understanding the spectrum of ring down modes that are produced in this coalescence. So here's an example of the kind of waveform that we get out of this. So the blue on top here, this shows the orbit. This is an example of an in-spiral from an orbit that was inclined at 60 degrees and it in-spiraled into a black hole with a spin of 0.9. I think this particular system had a mass ratio of about 1 on 1,000. So far beyond the regime of what LIGO and other instruments are now measuring, but is the kind of thing where black hole perturbation theory gives us some reliable insight. So you can see a fairly simple in-spiral waveform with a structure that's really governed by modulations between the axial and polar motions as the radius shrinks over the in-spiral. At a time greater than about, sort of arbitrarily labeled 0 on this thing, the waveform becomes more ring down looking. And an interesting feature you can see here, we look at it in 2 different viewing angles. So when we look at this face on, which means in other words, we're looking down the spin axis of this black hole, it's a pretty simple structure. It's a lot rattier and more complicated when we look at this edge on. It would be somewhere intermediate to those 2 things. We looked at it somewhere between the equatorial plane and the black hole spin axis. And what we're seeing here is the influence of all the different LM modes that are contributing to this final ring down radiation. So how do we actually characterize this? This is, again, a little bit of a technical point, but this is an important one for understanding the way our analysis works. So let's say we take the raw waveform that comes out of our black hole perturbation theory code. We decompose this on the unit sphere into a set of spherical harmonic modes. Now, here's an important technical point. Black hole quasi-normal modes have an angular dependence that is actually not, their natural angular functions are not spherical harmonics. They're a set of functions known as spheroidal harmonics. So each one of these omegas and taus corresponds to a different spheroidal harmonic, describing the angular distribution of that radiation. So our goal is to find, if you look at this equation I've written down here, I seem to have lost my cursor, unfortunately. We want to find the amplitudes, these script A's, and the phases phi that characterize the modes that are present in my data. So the way that we do this is, like I say, we start with the waveform decomposed into spherical harmonics, and then we go through and using a time frequency analysis, we determine which one of the modes actually is contributing, which one of these different modes that are produced by people like Berti, Cardozo, and Staranietes is contributing to the waveform that our simulation produces. So we go through a particular example to show the way this routine works. So I'm showing you here some raw data that comes out of one of our black hole perturbation theory calculations. Suppose we say, let's try to fit this with the 2-2 spheroidal mode. What you can see is that the mode amplitude that comes out as analysis is oscillating with time. It's not a very large amplitude. So this is telling us that the 2-2 spheroidal mode mostly fit that 2-2 spherical mode, but there's a little bit of dirt left over. So let's do both the 2-2 and the 3-2-2 modes. Excuse me, and the 3-2 modes. Now we can see that the 2-2 mode has really flattened out, at least until the signal becomes noise dominated. We appear to have fit that pretty well. And the 3-2 is not bad. There's actually a little bit of oscillation there as well. So we'll then do the 2-2, 3-2, and 4-2 modes. That turns out to be the best of all for this data set. So what we do is we sort of fit modes over a wide spectrum of different cases over and over and over again. And then we kind of develop just a pipeline for doing this analysis of what the ring down modes look like for these high mass ratio coalescences. Here's one example of the way things look. So here is the way that the 2-2 spheroidal mode looks for a particular family of in spirals. So what is interesting here is look at how much variation there is in this range. Okay, every single one of these cases corresponded to a binary, the mass ratio of 1 on 1,000, orbit was inclined at 60 degrees, the big black hole had a spin of 0.5. But we had different values for the accidental phase at which the small body plunged into the black hole. And you can see that the amplitude varied by about an order of magnitude over this regime in doing this. You should also see that every one of these points is doubly valued. This corresponds to whether the small body had increasing theta angle as it went into its final plunge or decreasing theta angle going into its final plunge. Again, it's just a function of an accidental phase. I had earlier made a claim that although our the world lines that go into making our sources, they vary depending on this sort of arbitrary parameter that ends our transition regime. The waveforms that come out of this were robust to that nonetheless. The reason is pretty easily described using this plot. Suppose I am choosing a particular value of the transition such that my thing ends at the value of theta fin that I've indicated with that blue dot. If I then use a slightly different value for that choice, what we find is it just moves us to a different value of theta fin, but it keeps it within that same family of excitations. So as long as our goal is just to understand the way in which this family of excitations depends upon the end state of the system, our analyses are robust and we can trust what our results are. So I'll just go back to the sort of big picture here. So this, this plot that I've shown you right here, pardon me while I skip through this again, you can think of this as just a two-dimensional slice through a family of excitations that really is at least five-dimensional. Okay, so here I'm showing sort of a three-dimensional slice of it, where I'm looking at the way that it behaves as a function of inclination angle, this accidental theta fin parameter, and at a particular value of spin. So we've developed catalogs that show the way this behaves for at least certain samplings of these many parameters. Here's a couple examples of them, looking at all of them for the same black hole spin, but now for different values of orbital inclination, different mode combinations. To my embarrassment, I noticed when I put this talk together that we appear to have switched our labels on some of these axes, but hopefully you can sort of see what the overall structure looks like. I'll just go through this quickly. Here's similar sort of two-dimensional slices for the L=3 mode excitations, a whole bunch more. You kind of get the idea. The punchline is that every in spiral excites a unique combination of ring down modes. And that mixture of modes depends very strongly, and most importantly, it depends deterministically on the binary's geometry, at least assuming general relativity is your underlying theory of gravity. It's certainly the case that when you have spin and orbit highly aligned with one another, that the in spiral is strongly dominated by the modes that have m equals L and m equals L minus 1. You can kind of see this over here on my plot on the left, where I'm contrasting an equatorial in spiral with a highly inclined one. When we have much more highly inclined cases, we get kind of, I almost like to call an ecumenical excitation. Basically, across all possible modes, things are excited in a much more even way. This sort of suggests to us that the inverse problem is at least plausible. If we can measure a spectrum of modes, we can do something about the binary geometry which produced it. And my student Halston Lim and I are sort of looking right now to see whether this is actually going to be feasible in practice. Now, we are doing all this, as I've kind of emphasized, in the large mass ratio limit, which is not the regime that describes the kind of binaries that are being measured today. I have kind of been hoping that this will inspire some of the colleagues in numerical relativity to start thinking about the way in which they characterize the late end states of the ring down, or excuse me, of the binary black hole waveforms that are being produced. And in concert with one of my postdoc, Lionel London, it looks like there are a lot of groups that are beginning to indeed look at that, which is, I think, an important step. I think despite the sort of limitations of the mass ratio restrictions that are in our study, there are some lessons we can take away that apply more broadly than in this limit. So first of all, this idea that it's going to be so important to fit modes beyond these kind of leading ones, that will surely hold beyond this large mass ratio limit in which we are working. And so that's going to be, especially as we start thinking about doing things like trying to test relativity with these waveforms, it's important to get that structure right so that we avoid systematic errors because we have not completely modeled our system. Incidentally, I have not talked yet, I've not mentioned this talk, things having to do with what are known as the overtone modes. It's a whole other kettle of fish, but there's been a lot of excitement lately about possibly the overtones playing a role in helping to probe the nonlinear nature of the merger and ring down waveform. And I think one has to be cautious because when you have misaligned cases like this, you can perhaps mistake some of these overtones for a more generic ring down mode that just happens to come from a misalignment. I also think it's a very important point that we found that when we parameterize this system using things depended so strongly on this kind of accidental phase parameter, and it really cleaned things up when we wrote that phase parameter in terms of the final state of the binary black hole system. When we initially started producing these results, we did what one always does when you're doing a physics analysis. You sort of parameterize things with some parameter that labels your initial conditions. And to be perfectly blunt, our results looked like crap. We could not tell what was going on. The amplitudes and the phases just had no discernible functional relationship to one another. They were scattered all over the place. And the reason for this was that there's kind of a mapping from initial conditions to final conditions. But to understand the final state of the system, it's really the final conditions that matter. There is presumably, in the large mass ratio limit, there's a well-defined angle at which my small body crosses into the event horizon. It's going to be difficult to come up with this sort of analog to that in the comparable mass case, but something like that may prove to be useful for cleaning up the behavior of things if one's characterizing ring down comparable mass coalescence. And finally, I do think that we are seeing from some of the work that's in progress right now is that it'll be really interesting to get the kind of information in these modes independently complementing other constraints we get from the waveform. There was a splash lately by people looking at the fact that you can sort of independently look at the mass and spin of the black hole at the end of the process and the mass and spin of the black holes at the beginning of the process and show that there's consistency with Hawking's area theorem. This is kind of in that sort of spirit in which you get very independent information from the end state that provides strong consistency tests on the information in the early state. And I would just advocate that there's a lot that can be done there. And I believe I am now done. So I'm not sure if I'm early or on time, but at any rate, I will stop here to take questions.
Thank you very much, Scott. Fantastic talk. Yes, we have 3 minutes for questions. So while people are thinking, Scott, I have an impractical question which couldn't happen in real life and probably only happens in science fiction. But if you had a sort of scattering experiment where you shoot one black hole into another, so that the end bit of the trajectory is sort of the plunge, but it happens relativistically. So that, you know, do you expect, I mean, obviously it's impractical, but do you expect any of this picture to change in the limit where, you know, the incident Lorentz factor is very high?
I'm pausing while I answer that because people have in fact done that sort of numerical experiment. You know, there have been, I'm thinking of some work that Franz Pretorius has done with some of his collaborators. They kind of have done the equivalent of the, you know, the high Lorentz factor collisions with one another. I don't know that there has been much work sort of exploring the way that depends, you know, on all the different kinds of parameters can be done. I know people have sort of looked at it as a function of impact parameter between the sort of centers of masses of these black holes and looked at the angular momentum of the system that is kind of left behind. I mean, the one thing which I'll remark, and it's sort of why when you extrapolate from our results to the comparable mass ratio limit, you run into a shortcoming, is that when you merge two black holes together, the final angular momentum of the system ends up, if the masses are if they're comparable to one another, then the spin ends up being dominated by the angular momentum at the plunge. That is not the case in the large mass ratio limit. And so, you know, unless you have a mass ratio such that, you know, you essentially remember the spin of the larger black hole going into it, a lot of what we're talking about here is kind of, you know, motivational, but almost aspirational, I would say. It doesn't quite describe the full physical problem. You know, and I think when you have a really high Lorentz factor like that, something similar happens. You're pumping in so much mass and angular momentum associated just with the collisional dynamics that it's a little hard for me to extrapolate.
Yeah, interesting. Yes, Marcus, please go ahead.
Hey, Scott, thanks for the talk. That was very interesting. Probably, hopefully, quite a simple question, but near the start, you basically say that you can take the phi dependence out of the PDE. I was just wondering if you've, you know, all the talk and the work is about the initial orientation. Is the final gravitational wave signal and the sort of shape of the inspiral not going to depend jointly on theta and phi? And yeah.
It certainly is, but in terms of just the structure of the differential equation that we need to work with, the point to be made is that because the background spacetime is axisymmetric, we can encapsulate our phi dependence very nicely in a set of simple basis functions, e to the im phi. It is, however, not spherically symmetric in general, and so we can't as easily break our dependence on the other angle. But you're absolutely right. We do still end up with the dependence in that. It's just that we have such a simple functional dependence for it that it simplifies setting up our mathematical analysis.
Okay, thank you.
Okay, thank you very much for the question. I think we are out of questions. Okay. And again, of course, please pop them into the chat box if they occur to you down the track, and Scott will answer them. Thank you very, very much, Scott, for the talk. And that brings us to our last speaker, which is Anna Volz, and she will be talking about measuring white dwarf masses with LISA.
Great. Okay. Can you see my screen?
Perfect.
All right. Hi, everyone. My name is Anna Volz, and I will be talking about measuring the individual masses of binary white dwarfs with space-based gravitational wave detectors. I'd like to thank my collaborators on this project, Kent Yagi, Nick Anderson, and Andy Taylor for their work. And I'll also note that this presentation is based off our paper published in MNRAS Letters. So the first measurement of gravitational waves with LIGO ushered in a whole new kind of astronomy. And one such system that we can study with gravitational wave astronomy are binary star systems. And in our analysis, we focused on binary white dwarfs. Future space-based gravitational wave detectors like the Laser Interferometer Space Antenna, or LISA, we'll be able to detect gravitational waves with its best sensitivity on frequencies around 10 to the minus 2 hertz. The frequency band is lower than that of LIGO, for example, because ground-based detectors have unavoidable Newtonian noise in this range. And some modeling has shown that there should be around 12,000 binary white dwarfs individually resolvable with LISA, which are represented by the gray dots in this plot here. And in our analysis, we focused on those systems with frequencies around this 10 to the minus 2 hertz range. Now, we've primarily focused on LISA in our analysis, but we also considered measurements with the decihertz interferometer gravitational wave observatory, which is another future detector that sort of bridges the gap between ground-based detectors and space-based detectors. So gravitational waves emitted from binary white dwarfs are nearly monochromatic, which means that the frequency doesn't change a lot. So the frequency and possibly its first time derivative are measurable. So the frequency and its time derivatives provide information about the source of a gravitational wave. And so if you can only measure these two quantities, the chirp mass is measurable, but not the mass ratio. However, if the frequency of the gravitational wave is on the order of or greater than 10 to the minus 2 hertz, it might be possible to measure the second time derivative, f double dot. And through that, we might be able to measure finite size effects on the gravitational waveform. So the two effects that we are talking about are the moment of inertia effect, which you get from a singular white dwarf spinning around on its axis, and the tidal effect, which is in the binary system, the gravitational pull of one white dwarf on the other, causing its shape to deform from the spherical model. So in our analysis, we show that if you can possibly measure these finite size effects, and if we can find universal relations relating these quantities, namely the moment of inertia I, the dimensionless tidal deformability lambda, and the mass of these white dwarfs, we can look at if these future gravitational wave detectors will be able to measure both the chirp mass and the mass ratio of binary white dwarfs. So if you can measure these two mass quantities, then you can resolve individually the masses of the binary white dwarfs in the system. So our first step was to write out how these finite size effects enter into our waveform. So here we have the orbital angular frequency of the gravitational wave omega and its first time derivative written here. And we have three effects that we included in our analysis. The first is the first order post-Newtonian correction, which you get from expanding the GR equations of motion. The second is the moment of inertia effect. And the third is the tidal effect. And so since the gravitational waves are nearly monochromatic, we can write out the gravitational wave phase as a Taylor approximation as shown here. So we first looked at sort of the magnitude of these three effects to see, are they all important? Do we need to include all of them in our analysis? So we just supplied three sort of example theoretical binary white dwarf systems of equal masses, as you can see here. And we looked at an observation period of 4 years by our detector. And as you can see, the tidal effect, phi lambda, can be close to half of the inertial effect. And for some systems, when the masses are relatively large, the first post-Newtonian effect can be on the order of the inertial effect as well. And so what this means is that we need to include all three effects in our analysis. We then tried to come up with universal relations between our quantities of interest. And we can do this because the equation of state for white dwarfs is more or less known. We assumed that our white dwarfs are cold, synchronized, and slowly rotating. And using binary white dwarf data, we fit relationships between the tidal deformability lambda, the dimensionless moment of inertia I bar, and the white dwarf mass. And as you can see, these relations are relatively insensitive to the atomic number Z. And with these two equations, we can now rewrite the gravitational wave phase in terms of the masses. So we no longer need to have, we don't need to separately find values for the tidal deformability and the moment of inertia. So with all these tools prepared, we used a Fisher information analysis to estimate the determination errors on the gravitational wave parameters. And we can do this because we are provided an accurate gravitational waveform as we derived in a previous slide, and assuming that our detector's noise is stationary and Gaussian. So as you can see here, the inner product of this matrix is dependent on the gravitational waveform, the derivative of that with respect to our individual parameters. So we considered, and the inner product also depends on the spectral noise density of the detector, the observation period of the detector, and these parameters that we have here. So we considered two sets of parameters that just sort of are two different ways to write the two mass terms that we have. So the first set of parameters that we considered is the chirp mass, mass ratio, the initial frequency of the gravitational wave f0, the coalescence phase of the gravitational wave phi0, and the amplitude of the gravitational wave. And then in our second set of parameters, we just solved for the mass of our primary white dwarf and the mass of our secondary white dwarf instead of having the chirp mass and the mass ratio. So we calculated the Fisher matrix for the first set of parameters, and I'll just sort of explain these graphs a little bit. So these graphs show the fractional error on the mass ratio, delta Q over Q. And we supplied an initial frequency of 0.02 hertz, a coalescence phase of 3.666 radians, and the color coding here is for a separation distance of 1 kiloparsec. And so we range then over various values of masses for these sort of hypothetical binary systems. And the reason only half the graph is shaded in is because the mass of the primary, M1, just by definition, is greater than the mass of the secondary. And so as you can see from our plot here, the fractional error, delta Q over Q, is less than 1 in most regions of this parameter space. So what this means is with LISA, it should be able to detect the mass ratio of a binary white dwarf if it falls sort of in this parameter space. And as you can see, comparing LISA to our plot with DeSigo, the measurability greatly improves with DeSigo compared to LISA. And this is because DeSigo has a greater signal to noise ratio with the supplied parameters. We also have on this plot our data for a separation distance of 10 kiloparsecs. So basically inside these dotted line regions, the measurability is less than 1, so the mass ratio is measurable. So the measurability, decreases when your separation distance increases, but there still are some regions where you would be able to measure the mass ratio. And so you'll also notice that we kind of have this interesting ring structure in our two plots. And so we looked into that, and basically because of the way that the Fisher analysis is set up, we believe that this is due to degeneracy between our mass parameters, namely the mass ratio and the chirp mass. So we repeated this for our second set of parameters. So here we have the fractional error on the mass of the primary, and we don't show the mass of the secondary graph because it's essentially the same. And so similarly, we have the same initial parameters. The color coding is for a separation distance of 1 kiloparsec, and we see the same results. The mass of the primary will be measurable in most regions of this parameter space. And so on this graph, the gray lines also represent just some values for DeSigo. And so you can see that with DeSigo, you get about a factor of 10 better measurability than with LISA. So what our results show is that for many binary white dwarfs, these space-based gravitational wave detectors will be able to determine the individual masses of these systems for specific scenarios. So just to summarize, we wrote out the finite size effects due to the tides and moment of inertia and added them to the gravitational waveform of a binary white dwarf. We found universal relations between the moment of inertia, tidal deformability, and mass of white dwarfs. And we use these in our Fisher analysis to show that the mass ratio and therefore the individual masses of many binary white dwarfs will be measurable with LISA and DeSigo. And now we did this for sort of specific initial parameters, but we showed also that this is a novel way to estimate the parameter errors, so you could apply this to other scenarios, whether you want to have different initial parameters or if you want to check the measurability of different parameters as well. So like I just said, you could use this to compare it to a population of simulated binaries to confirm our results and, sort of plug in specific scenarios if you want to see if those detectors will be able to measure the masses. You could also fold in the effect of our uncertainties and our universal relations into our analysis and extend our analysis to asynchronized binary white dwarfs. Yeah, if there are any questions, I'd be happy to answer them.
Thank you very much, Anna. Thank you for keeping to time. Questions, Fran, and the first one is from Scott.
Hi, and it's a very nice talk. I'm curious, there's a really interesting structure I saw, and can you go to I think it's the previous slide will be good enough. There we go, that one. So you have this sort of zone, the zone of red has this really interesting shape that, I'm looking at the way it sort of goes up from the lower left corner and then kind of swoops down. And so there's these two islands where things are measured particularly well. One of them appears to be, close to roughly equal mass. One of them is a little bit larger mass ratio, essentially. Is there sort of, a simple explanation of what competing effects are sort of driving why it works well there and drives to the, you wind up then with this interesting structure where it doesn't look so good sort of between the two of them?
Yeah, that's a great question. So I think you're sort of talking about these purple regions, is that right?
Actually, the purple region and then the one a little bit below, so there's a big purple region there in the upper right, and then there's one sort of below it. And I'm just really curious about that sort of red leg that goes between them there.
Yeah, so that structure, so if you look at the Fisher matrix, right? If you're looking at the measurability of Q, so say that our theta I is our Q parameter. So we looked at this and thought, okay, so maybe this has something to do with the derivative of the phase with respect to Q. And so we looked at that a little bit further. And so the main term contributing there is, contributing into the phase is the first derivative of the frequency f dot. And so we looked at df dot dq and where that equals 0. And it does follow this line sort of for a little bit, but then it deviates. I didn't include it in this PowerPoint, but it sort of follows some of these lines. So it sort of explained half of, why this was. And then, like I mentioned before, you also have to take into account correlations between the other parameters. So the elements of the matrix affect each other as you're doing this analysis. And so we also looked at, which parameter sort of is causing the mass to go this way. And basically, if you look at the measurability of Q without correlations between parameters, it follows very well the df dot dq equals 0. But then once you combine this Q parameter with the chert mass measurability, that's when you start to get this ring parameter. So we've sort of narrowed it down to something to do with how the two mass terms interact in our waveform. I hope that answers your question.
Yeah, that's good. Thank you.
Thank you very much. The next question from Alexander, please.
Hi, first of all, great talk, Anna. So if I'm reading these plots correctly, this is basically saying that for most of the parameter space, you can get about a 30% error out to about 1 kiloparsec.
Yeah, I think so.
Okay. So does it look like you're only going to be able to do this for kind of the local neighborhood, or have you looked at how well you can measure these things once you get out to kind of the rest of the galaxy?
So the separation distance is between the two stars. It's not between the system and the detector yet. So the separation distance is from one white dwarf to the other.
Gotcha. And that's a kiloparsec?
Yeah.
Okay, thank you very much. I don't see any other questions. We do still have a bit of time. I don't see anything in the chat. Anna, I might just ask something. Apologies again if it's naive, but is there any scope for extending this to, for example, measure compositions or internal structures of these objects, or are they just too far apart to for any of those couplings to matter?
That's a good question. I will start off by saying I'm not really sure. I think that you could do a similar sort of Fisher analysis for different kinds of parameters. So if you could, the sort of beginning of this project, the people that worked on it before me, they were looking at if you could measure, for example, the moment of inertia of a white dwarf. And so you could, if you figure out how it enters into the waveform, you could perform a similar analysis. And instead of having, your parameters be mass parameters, you could, for example, here, rewrite the mass in terms of the moment of inertia, or you could rewrite the tidal deformability in terms of the mass. And so, or other way around, I forget what I said. But for example, like if you write your waveform then in terms of what you're interested in, then I think you could very easily perform a similar analysis and get, how well will I be able to measure the tidal deformability, or how well will I be measured? Well, how well will I be able to measure the moment of inertia? Is that what you're asking?
Yeah. No, that makes sense totally. Thank you. Fantastic. All right. Well, if there are no more questions, then let me just finish very briefly by thanking everybody very warmly for coming to the session, and also a massive thank you to our speakers for sticking to time and giving great talks. The next GW1 session is tomorrow at, I'm a bit confused about times right now, but I think it's tomorrow morning, Northern Hemisphere time, or Eastern Hemisphere, whatever it is. And I also just want to finish by thanking very much the co-hosts who made sure that Zoom didn't crash. So yes, thanks again, everybody, very much. And
Andrew, I'd like to thank you for staying up way past your bedtime and us running smoothly here.
It was a pleasure. My eyes didn't droop once because the talks were awesome. All the best, everyone.
Cool. Thanks, Andrew.
Thanks, all. Take care.